What's up, everybody, and welcome back to another video from the Scalar Learning channel. This one is a massive video. We are doing everything that you need to know for the digital SAT, all of the critical concepts in one video, categorized by the 4 big categories. We're starting with category 1 of 4. This is every critical concept you need for the algebra-based question. So without further ado, let's do it. So first of all, let's go through the subcategories for algebra. We have solving linear equations and inequalities, linear equation word problems, linear relationship word problems, graphs of linear equations and functions, solving systems of linear equations, systems of linear equation word problems, linear inequality word problems, and graphs of linear systems and inequalities. So now we're going to step through the critical concepts for each of these subcategories. Let's go. So for solving linear equations and inequalities, it's very important to understand inverse operations when we're conducting variable isolation. An inverse operation is basically a way to think about an opposite operation. So inverse operations for plus, times, square root, and sine, just as an example, would be as follows. For plus, the inverse or opposite operation is subtraction. For multiplication, it would be division. For taking a square root, it would be squaring. And for these trig functions like sine, cosine, and tangent, it would be arc sine with that little -1, arc cosine, arc tangent. Now to put this into practice, when we're actually isolating a variable, we want to use these inverse operations with the principle farthest first, meaning we're removing numbers that are farthest away from the variable first. So let's see how that works with this equation. So right here, we've got a 2 multiplying the x. We've got a radical of the x. We're dividing by 3, and then we've got a plus 19. So the farthest operation is this plus 19. So we're going to start by doing the inverse of that, which is minus 19. So I'm going to minus 19 from both sides like so. 21 minus 19 is 2. Now then we see that we're square rooting the x, we're multiplying it by 2, and then we're dividing by 3. So dividing by 3 is the next farthest thing away. What's the opposite of dividing by 3? That is multiplying by 3. So as this cancels out, now we have 2 rad x is equal to 2 times 3, which is 6. Now the multiplication 2 times rad x is the next farthest thing away, right? The radical is the closest thing to the x, so we're going to do the opposite of multiplying by 2, which is dividing by 2. So now we've got square root of x is equal to 6 divided by 2, which is 3. Now we need to get rid of that square root. The opposite of square root is squaring, so we're going to square both sides like so. That's going to kill that radical, and we have x is equal to 3 squared, which is 9 for the win. Boom, done. So that's how you put these principles into action. Hope that makes sense. Next, we're going to talk about combining like terms when there's more than one instance of the variable, like in this equation, for example. So yes, once again, we want to isolate, but we have an initial step here that we have to take care of first, which is consolidate, meaning combining like terms. So 3x plus 2x, that's saying like 3 oranges plus 2 oranges. It's the same thing. You want to think about the variables like items. So 3x plus 2x is 5x, and then we have 5x minus 18 is equal to 22. Now we're going to follow those same principles. The minus 18 is the farthest away, so we're going to do the opposite of that first. We're going to add 18 to both sides like so, and then we have 5x is equal to 22 plus 18, which is 40. Now we want to get rid of this 5. The 5 is multiplying. We do the inverse of that, which is divide by 5 like so. 40 divided by 5 is 8, and we have 8 for the win. Boom, done. Now we're talking about how to solve a linear inequality. So again, we're using the principle of variable isolation to get a solution. Let me show you how that works. So once again, we're going to minus 16 from both sides, right? Doing that inverse operation, and then we have 4x is less than 32 minus 16, which is 16. Now we're going to divide both sides by 4 like so, and we get x is less than, don't forget to keep that inequality, don't change it to an equal sign. X is less than 4. So this gives me my solution set. It's not a single solution. It's saying any value less than 4 is going to satisfy this inequality, meaning 3.3, 0, -1,000,000, etc. Now, another rule that's very important when we come to inequalities is when you divide or multiply both sides by a negative, you must flip the inequality symbol. So in this example here, we have an inequality. Let me show you how that rule takes place. So when we have a plus 17, we're going to again isolate by minusing by 17 on both sides. Then we have negative 3x is greater than negative 7 plus negative 17, which is negative 24. Now I'm going to divide by a negative. So as I mentioned in the previous slide, when we divide by a negative, we have to flip the inequality, which means we're left with x is less than negative 24 divided by negative 3, which is 8. So our solution set is any value less than 8. Boom, done. Now we're on to linear equation word problems. So I want to go over these critical values that are very important for linear equations. So for example, we have slope of a line, and slope of a line is always going to be my rate of change or cost per unit. It's going to be one or the other when we're looking at these linear equation word problems. We also have the y-intercept. This is a very critical point as well, and this is our starting point or initial value. Last but not least, we have the x-intercept, and this is going to be the point of zero value, or when y goes to 0. Now, in our standard slope-intercept form, which is y equals mx plus b, you can see that in this format, we can readily see what the slope is and what the y-intercept is. Now, as we look at this example problem, we can identify the correct equation based on these principles. For a training program, Juan rides his bike at an average of 5.7 minutes per mile. With that per word, we know that this is indeed a rate. Which function m models the number of minutes it will take for Juan to ride X miles at this rate? So again, since we know that this is the rate, this should be the slope. So what I should be seeing is 5.7x. Now our y-intercept might be, hey, the distance that we've already traveled at time 0. They don't give us any value for that. So I don't think we should see a y-intercept, meaning that this right here should be the answer. So again, in red, that is our rate. And again, we can confirm that D is indeed the answer. Now we got a second example here. Hannah deposited a fixed amount into her bank. The function f of t equals 100 plus 25t gives the amount in dollars in Hannah's bank account after t monthly deposits. What is the best interpretation of 25 in this context? Again, 25 is next to the variable. Even though it's out of order, we still see that 25 is some sort of representation of a rate. So we're going to highlight that in red, and then the correct answer choice should be describing this as a rate. So what I'm thinking is this is the rate of deposit per month, right? Because it's multiplying that t value. Now, what about 100? What is 100? 100 is our y-intercept. So if they were asking about 100, I should expect to see an answer choice that says this is the amount of money that she started with, $100. Again, that's the initial value. Now, the one answer choice that is dealing with 25 as a rate in terms of the amount of that monthly deposit is A. It says each monthly deposit, the bank account increased by 25. That's the rate of change. So every month, the bank account is changing positively by 25, meaning A is the winner. Now, just so you can see, answer B would be a great answer if they were asking about the $100, right? Before Hannah made any monthly deposits, the amount in her bank account was blah, blah, blah. That's the initial value. Now, again, if they said 100, this would be good to go if we were talking about 100, but they're talking about 25, which is the rate. This one, we have another example. It says the total cost in dollars to lease a car for 36 months from a particular car dealership is given by this function, where X is the monthly payment in dollars. What is the total cost to lease a car when the monthly payment is $400? So this is a situation where we're doing a little plug and chug. So since they're saying that X is the monthly payment, they're saying that this 400 is going to be plugged in for X. So let's plug it in and evaluate. So we'd have 36 replacing X with 400 and then adding 1,000. So 4 times 36 is 144. Add those two zeros, 14,400 plus 1,000, which would give me C, 15,400. That's how you do it. Done. Now we're on to linear relationship word problems. The number in front of each variable is the rate per variable. So this is very important for a specific type of question that we're going to see on the digital SAT many, many times. So let me show you. A teacher is creating an assignment worth 70 points. The assignment will consist of questions worth 1 point and 3 points. Which equation represents a situation where X is the number of 1-point questions and Y represents the number of 3-point questions? So what we should see is, since we see 1 per X and 3 per Y, we should see 1x plus 3y. This is giving the total amount of points for X added together with the total amount of points for Y. Now, if you think about this, this makes a lot of sense, because think about it. X represents the number of 1-point questions. So if I get 5 1-point questions, I should get 5 points. Hence, X, the actual number of the questions, would be equivalent to the point value. What about for Y? If I have 5 questions for Y, that should be 15 points, right? Because 3 points per question, 3 times 5 makes sense. So that's why we should see X plus 3Y. And then this should equal that total point value of 70, which means that the correct equation equaling 70 is going to be D, because here we see X with a 1 in front of it, again, an invisible 1, Y with that nice 3 in front of it, meaning D is the winner. done. Now we got a second example. It says Jay walks at a speed of 3 miles per hour, a nice rate, and runs at a speed of 5 miles per hour. He walks W hours and runs for R hours for a combined total of 14. Which equation represents this situation? So once again, we see that total occurring in A and B correctly, meaning we can eliminate C and D. Now we have that rate. Rate times the time is going to give us that total distance. So the appropriate option is going to be shown where we have 3W is going to be in option A. Likewise, for this R hours at 5 miles per hour, we should see 5R, which again we see in A, which means A is the winner. Done. Now we're going to talk about graphs of linear equations and functions. So here, for example, the general graph of these linear functions are always going to be lines. Here's an example of y equals 2x. We got an example of y equals x plus 3 with that nice coordinate shown there of -5, -2. And then we've got this one, y plus 3 equals -3/4 x minus 4. Again, the thing that all of these have in common is the degree of y and x are always both going to be 1 in this case, right? The top two are in slope-intercept form, which we're about to go over, and the bottom one is in point-slope form. So now again, when we go back to these critical values that we identified previously, what they look like on the graph in terms of slope is going to be rise over run from any 2 points. So I arbitrarily selected these 2 points, and the slope is going to be how much does it go up versus how much does it go over, and it's the ratio of those two values. And again, slope is synonymous with rate of change. We also have the y-intercept, and again, that's that blue dot where it hits the y-axis. So the y-intercept, which again we know is occurring at 0y, don't forget, is our initial value. And then last but not least, we have the x-intercept, which is where it hits the x-axis right there, and in this case, the value of y is 0, so it's going to be occurring at x, 0. Now let's talk about slope-intercept form. This is the most common formula and format for a linear equation on the SAT. So y equals mx plus b. Again, m is the slope, b represents the y-intercept, and slope, as we mentioned in the previous slide, is rise over run. So if we want to look at a graph and see how this manifests, right, we've got these 2 points. That's again going to give me the slope, that rise over run, and my y-intercept is again where this is hitting the y-axis. Now we're going to do an example of an equation in slope-intercept form, y equals 2x plus 3. Again, my slope is going to be that 2, right? 2 over 1. You can find that at any 2 points that you select. It's going to have a 2 rise and a 1 run. Now again, if we chose points a little farther away, well, you might say, well, then we're going up by 4 and going over by 2. But if you put that into a ratio and reduce it, it's going to reduce to 2 over 1 again. Now here we see the y-intercept occurring at 0, 3, and that matches with this value of 3 as the y-intercept. Now let's talk about point-slope form, which is another format that linear equations might occur in, and it's another format that you can use to derive the equation of a line given a point and slope. So for example, point slope form is y minus y1 equals m times x minus x1, where m is once again the slope, but now what is x1 and y1? It's any point. You can take any point of a linear equation, plug it into this format, and you're going to get a legitimate linear equation for that line. So now let's see an example in action. So we see that we have y minus 3 equals 2/5 times x minus 2. So we can tell right off the bat that my slope is 2/5, and the point that is within this equation is going to be +2, +3, right? So the point is kind of the opposite of these values. If it's minus, then it's going to be positive. If it's plus, it's going to be negated. So there we see our point 2, 3. We can also represent linear equations in standard form, which you might see sometimes on the SAT. Now, you don't have to know all the restrictions for standard form, but it's good to recognize standard form and some of the basic principles. So standard form is ax plus by equals c. So basically what you can see is we have the variables on one side and the constant on the other. And a, b, and c must all be integers, and a must be positive. Okay, so those are the main restrictions for standard form. So just as an example, this is an equation in slope-intercept form. This is the equivalent form in standard form. Now to go from slope-intercept form to standard form, basically we're going to start by moving the 2/3 x over to the other side. So I'm going to add that to the other side. So we'd say, all right, now we have 2/3 x plus y is equal to 7. We're almost there, except we don't want a fraction, right? We mentioned that we want no fractional coefficients or constants. So how can I turn that into a nice whole number? I can multiply the entire equation by 3, right? 3 times 2/3 is 2x, 3 times y is 3y, and 3 times 7 is 21. And that's how we get to this equivalent standard form of the linear equation. Now, as we graph this out, we see that we have that y-intercept of 0, 7, which we saw in this equation, and that slope of negative 2/3, we can see it right here, right? We're going to go down 2 to the right by 3 to get to the next point on the line. Now let's talk about solving systems of linear equations. There's a few ways that we can solve systems on the SAT. So the first way is the algebraic method of substitution. So let's say we have this system. Let me show you how substitution works. So when we're substituting, I see that y equals 2x plus 1 in this linear equation. Well, I could substitute it in for y in the second equation. So now I'd have 2x plus 1 is equal to negative 2/3 x minus 7. Now, since I have a single variable equation, I can solve for x. How I would do it here is I don't want to deal with that fraction. So I'm going to multiply everything by 3, boop, 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 and boop. We'll distribute that there. We get 6x plus 3 equals 3 times negative 2/3 is negative 2x. 3 times negative 7 is negative 21. Now I'm going to add 2x to the other side, and that's going to give me 8x. Let's simultaneously subtract 3 from both sides as well. So that's going to destroy that. And we have negative 21 plus negative 3 is negative 24. Then we're going to divide both sides by 8. And we get negative 3. So I know my solution is now negative 3 something. Now to get that corresponding y value, I can plug it in to either equation. Let's plug it into the top one. Negative 3 times 2 is negative 6 plus 1 is negative 5. And there's my solution, which also represents the intersection of these two lines. That's how you do it with substitution. Done. Now we also have elimination. I'm going to show you how to do elimination method for these same two equations as well. So elimination, we just want to eliminate one of the variables. So what I'm going to do is, since I both have one y and one y, I can negate this second equation. And by the way, the double negative turns into a positive here and here. Now I'm going to add these together. Y plus negative y is 0. Then we have 2 plus 2/3, which is 8/3 x. And then I have 1 plus 7, which is 8. Now I can solve for x. I'm going to isolate x. So I'm going to subtract 8 from both sides. Negative 8 equals 8/3 x. And then we're going to multiply by the reciprocal to isolate, right? Multiply by 3 over 8. It's the same as dividing by 8/3, okay? That's going to cancel out on that side. And negative 8 times 3/8 is negative 3. So again, we get negative 3 for x, and you plug it back in, and you get negative 5 for y. And this is good, right? Because we have two different methods that give us the same answer. They're both correct. And that's how you do it with elimination. Now, the last way to solve it is Desmos. I'm going to show you how to solve a system with Desmos here. Now, you might say, well, wait a minute. If we can use Desmos, why do we even need to know elimination and substitution? Well, I'll say that a lot of times I think Desmos is the way to go. It's going to be pretty quick and pretty easy. But the reason why it's great to know substitution and elimination is because sometimes they may throw another variable constant in the mix or some other modification where the algebraic method is actually going to be easier to solve on the SAT. So I'm just giving you different options and different methodologies. And again, sometimes substitution may be just plain and simple faster. So there you go. But now let's check this out in Desmos. I'm going to graph these two equations. So here are the two equations, and you can see the intersection point is right here. And again, that matches up with what we got before, negative 3, negative 5. So in every situation, we're getting the same answer. That's what we like to see. So now we're going to talk about some of these interesting questions where they might say, find a constant such that the system is of a certain nature. So what are the options that they're going to give you in this case? They're either going to say, hey, where the system has no solution. So what does no solution mean? Immediately, I want you to think same slope, different y-intercept. So here would be an example where they both have a slope of 3, but they have different y-intercepts. These are going to be parallel lines. That's why there's no solution, because the solution occurs when the lines intersect. And as we know, parallel lines never intersect, okay? Or they'll say, find a constant such that the system has one solution. This simply means different slope. We don't even care what the y-intercepts are. If the slopes are different, they will guarantee to have one intersection point at some point. And then the last option is they say, find a constant such that the system has infinite solutions. That means same slope and same y-intercept, meaning they're exactly identical. And this is an example here, right? Even though these equations look different, if you put the bottom one into slope-intercept form, meaning dividing both sides by 2, you'd see that they're the exact same equation. And on the graph, it would look like this. It would look like one graph, and that's because the blue is on top of the red, so that's why we only see one line. So remember, when you get a question like this, the constant needs to be a number such that it makes one of these three scenarios true, depending on what the question is asking about. So if they're saying one solution, the constant has to be something that's going to give us different slopes. Now we're moving on to systems of linear equation word problems. And again, essentially all we're doing is we're trying to generate a system of equations. And then once we do that, we can solve it algebraically or via Desmos. So this is a mixture problem, which is pretty tricky. And I did see them crop up on a recent PSAT. This is from one of the College Board PSATs. So I just want to show you how to solve one of these mixture problems. And this one is pretty difficult, so it's a great example. So we see that the sample has a mass of 50 and is 50% silicon, right? And then we've got two pieces of different alloys. The first is 30% and the second is 80%. So I'm going to make a little table here. I'm going to say 30% is X, and we're going to say the 80% one is Y. And let's see if we can make a nice system. So I know that the mass of X and Y together is equal to 50 because that's the total mass, and X and Y represent the total mass of the 30% and the 80%. So we have our first equation, X plus Y is equal to 50. Now the second equation, we're going to do it in terms of the silver in each of these alloys. So X, it's 30% silver, or silicon, excuse me. So we have 30% times X plus, and then Y is 80% silicon, so 80% times Y. That gives me the total amount of silicon in each of these. Added together is equal to the total amount of silicon in the final product. Now I know the total in the final is 50%, but the question is 50% of what? Oh, I know the total is going to add up to 50, so I can say equals 0.5 times 50. Now I have this beautiful system of equations and I can solve it whichever way I want. I'm going to show you how to solve it in Desmos just for fun. So I'm going to write these in and let's see what we get. So I type these in just as is without any modification, and I see this beautiful intersection point where X is equal to 30, Y is equal to 20. So we know that X is equal to 30, Y is equal to 20. So is my final answer simply 20 because they're asking about the second piece, the 80% piece. But notice they have one little trick up their sleeve. They said, what is the mass in grams of the silicon in the second piece, right? So the second piece is 20 grams, but they said, what's the mass of the silicon? Well, that's 80% of that 20, right? So this just has one extra trick that I just want to point out. So the final answer would actually be 16 for the win. Done. So in this one, we have another example. So let's read it out. Hero and Sophia purchased shirts and pants from a store. The price of each shirt purchased was the same as the price of each pair of pants. Hero purchased 4 shirts and 2 pairs of pants for 86. Sophia purchased 3 shirts and 5 pairs of pants for 166. And again, it says X represents the shirt and Y represents the pants. So what we should be seeing here in the correct answer is 4X plus 2Y equals 86 as one equation, and the other one would be 3X plus 5Y equals 166. Because again, X represents the price of each shirt and Y represents the price of each pair of pants. So again, here's our equation of the first one that I pointed out, right? 4 and 2 equals 86. And I see that in option A, right? 4x plus 2y equals 86. And for the second equation, it's 3 of x, 5 of y equals 166, which again, I see in option A. So this is how you would do a problem like this, where you're just trying to set up the equations, not necessarily evaluate them. Now we're moving on to linear inequality word problem. So we're going to do another example here. And again, we don't have to evaluate, we just have to set it up. So it says, Valentina bought 2 containers of beads. In the first container, 30% of the beads are red. And in the second container, 70% of the beads are red. Together, the containers have at least 400 red beads, which inequality shows this relationship. So X is the number of beads in the first container and Y is the number in the second. So again, just color coding appropriately, we see that 30% should be of X, 70% should be of Y. So when we see percentages in equations, I should see the decimal equivalent, meaning 0.3 and 0.7. And I see those in option A. Now we come to the at least 400 red beads, right? So what is at least? You want to think if it can be at least 400, it could be 400. It could also be 401, 410, 520, etc. So we should have those that variable expression being greater than or equal to 400. Hence, A is the winner. Done. Now, just to give a quick overview of these different words implying different inequalities, more than or greater than would imply the greater than symbol, right? Greater than or equal to, at least, no less than. These are all saying greater than or equal to symbol. You might see less than or smaller than. That's simply the less than symbol. And finally, less than or equal to, or it could be said as no more than, or at most, now we're talking about less than or equal to. Now we're on to graphs of linear systems and inequalities. So as we mentioned before, right, when we graph an equation, y equals 2x plus 1, and a second one, y equals negative 2/3 x minus 7, once again, our solution set, as I showed you in the Desmos example, is going to be that intersection point. And here they intersect at -3, -5. And by the way, these are the same equations that we were looking at previously. Now, when we graph an inequality, it's not just a line, it's also going to be a shaded portion. So let me show you how this works, right? Let's say we have y is greater than -2x. What should this look like? Well, first of all, we're going to create the line y is equal to -2x. But you might say, why is it dotted? When it's greater than or simply less than, it's going to be dotted because we're not including the line as a solution set. We would include it if it says greater than or equal to or less than or equal to. Okay, so we know it's dotted. Now, there's a shaded portion that is going to be the solution of this inequality. How do we figure out whether we shade above or below? Based on the inequality and the direction it faces with respect to y. So here it says y is greater than -2x. That means we shade everything above the line. So don't think left and right, think above or below. So what would a potential solution be? Anything in the shaded region. For example, 9, 1. And you can see if I plug in 1 for y and 9 for x, I get 1 is greater than -18. That is, of course, true. Another example would be 5, 5. Again, you plug in 5 here, plug in 5 there. 5 is greater than -10. Again, that's true. Now here's another example. Y is less than or equal to x plus 1. Again, we should now see a solid line, and that line is the same as y equal to x plus 1. And since it says less than, we're going to shade below. And so now let's look at some possible solutions. We've got 2, 1, which is in the shaded region. Again, you plug it in. 1 is indeed less than 2 plus 1. Another example is 5 and -5, right? -5 is indeed less than or equal to 5 plus 1. Now let's talk about graphing a system of inequalities. So a system would be two inequalities. So first we have y is greater than -2x, which we've shown here, right? And then we have y is less than or equal to x plus 1, which we showed previously and now we've shown here. So what is the solution set? The solution set to a system of inequalities is where the shaded regions overlap. So we know we have shaded region here for one of them, but not both. Shaded region down here for one of them, but not both. But in this section out here, we have both sections shaded. So one possible solution would be 7, -2, and that would satisfy both inequalities. Another one would be 8, 3, and a third one would be 5, 6. Now 5, 6 is interesting because it's within the shaded region, but it's on the purple line. And the reason why that's acceptable is because it's less than or equal to, meaning solutions on that actual line are going to be legit. So we can try it out, right? 6 is less than or equal to 5 plus 1. That 6 is less than or equal to 6. That's true because of the or equal to. They are allowed to be equal, and that still works. And then we plug it into the other one. 6 is greater than or equal to -10. That, of course, does satisfy the other inequality. Now, a common question that they always love to ask on the SAT is, are the following solutions? And they might go through different options like this. So the way you could do it either graphically or algebraically is as follows. So graphically, you could look at the system and plug in these points. Be like, oh, 1, 1, yep, it's in the double shaded region. What about 2, -3? Yep, it's in the double shaded region. What about 5, 7? No, that is outside of the double shaded region. Therefore, it doesn't work. Another way you could do it is you could plug these in to these inequalities one by one. And that's often how I like to do it. So for example, let's try the 5, 7, which we know fails. Is 7 greater than -10? Yes. So it satisfies the first inequality. But what about the second one? Is 7 less than or equal to 5 plus 1? No. 7 is not less than or equal to 6, and that's why it doesn't satisfy both inequalities. That's it for critical concept 1, algebra. Now it's time to move on to section 2. Now we are moving on to problem solving and data analysis, which is part 2 of 4 for critical concepts. Let's go. So for problem solving and data analysis, we're going to be covering the following subcategories. So first we have ratios, rates, and proportions. And next we're going to go on to unit conversions, then percentages, center, spread, and shape of distributions. This is going to look at things like median, mode, and mean. We've also got data representations, scatter plots, and that's going to include line of best fit, linear and exponential growth, probability and relative frequency, data inferences, and last but not least, evaluating statistical claims. So as we jump into ratios, rates, and proportions, first of all, what is a ratio? A ratio can be expressed as a fraction, like 1/2 or 1:2. We could also represent it with a colon, right? 1:2, or you can literally say 1:2 as well. Now we also have 4/9 or 4:9, which can be also represented as 4:9, and 2/5 can be represented as 2:5, and last but not least, 3:7 or 3/7 can be represented as 3:7. A common question that they might ask on the SAT is, what is the ratio of AB? And what they're going to do is they might give you an equation like this: 3A is equal to 7B. So again, since we know that A to B can also be represented as A over B, we can try to get this into that format. So first, to get A over B, I'm going to divide both sides by 3 to isolate the A, and that's going to get rid of the 3 on the left-hand side. And now we've got A is equal to 7B over 3. Now I want to get rid of the B on the right side because I want it to be A over B. So we're going to divide both sides by B, canceling that out. And now we can see that the ratio of A to B is 7:3 or 7/3. And presenting it in this colon format would be 7:3, boom, done. Next, we're going to get into rates, right? Rate is something per something. The most common example is speed, miles per hour. And that means that we got to know the formula: distance equals rate times time. This is a very, very important formula, even though you might think, well, it's a little bit basic, but despite that fact, it's very important. D, of course, is distance. We've got R is equal to the rate, and T is equal to the time. And again, our example of rate would be miles per hour. We might also see an example of dollars per pound, but the key is that word per. Now here we have a rates question. It says Laura can swim 2 laps in the local swimming pool every 1.5 minutes. At this rate, how many minutes does Laura need to swim 12 laps? So again, let's use distance equals rate times time to solve this equation. So we have a distance of 2 miles. We have a time of 1.5 minutes, and the rate is what we need to figure out. Well, we now have this great equation. Let's divide both sides by 1.5. R equals 2 over 1.5. That's the same as 4 over 3, right? If I double that. So now we've got this really nice rate. And now we're trying to see how many minutes, meaning solving for time, when we know the distance is 12. So check this out. I'm going to plug in 12 for D, and I'm going to plug in my rate of 4/3, and now we're solving for our unknown value of time. And now all we got to do is isolate, right? To get rid of the 4/3, we multiply by the reciprocal, which is the same as dividing by 4/3. That is 3/4. We're going to multiply on both sides. This is going to cancel out to 1. And then 3/4 of 12 is 9. So that means T equals 9, which means it will take 9 minutes. Boom, done. Now let's talk about proportions. Proportions, okay, is like a fraction equaling a fraction, like A over B equals C over D, right? And these equations can be solved via cross multiplication. So here, if we know that A over B is equal to C over D, we also know that B times C is equal to A times D. Now, let's say we have an equation that is comprised of a proportion. We know that 1 over 3 is equal to x over 9. To solve for x, once again, we're going to cross multiply like so. 1 times 9 is equal to 9. On the other side, we have 3 times x. So now we have 3x is equal to 9. Divide both sides by 3, and we get x is equal to 3 for the win. Done. Now we're going to use a proportion to solve the following question. So it says if 7 pounds of plums makes 8 fruit rolls, how many pounds is needed to make 20 fruit rolls? So let's check this out. I'm going to set up a proportion, but before I do, I'm going to label it. And this is arbitrary. I'm putting plums on top, rolls on the bottom. Could I do the opposite? Absolutely. But I'm choosing to do it this way just because. So now we've got plums on top, and we're going to set up our proportion. Now it says 7 pounds of plums makes 8 rolls. So how many pounds of plums, which is x, is needed to make 20 fruit rolls? Now we got this beautiful proportion. Now let's solve. We're going to cross multiply. We've got 8x is equal to 7 times 20, which is 140. Then we're going to divide both sides by 8, and we've got x is equal to 17.5, which means the answer is 17.5 pounds of plums. Done. Now we have another problem. It says to make 4 batches of cupcakes requires 7 tablespoons of sugar. How many tablespoons is required for 5 batches? Okay, once again, we're going to go batches on top, arbitrary, tablespoons on the bottom, arbitrary, and we've got our proportion. So we've got 4 batches requires 7 tablespoons. So to make 5 batches, how many tablespoons do we need? Let's cross multiply and solve. So we have 4x is equal to 5 times 7, which is 35. Divide both sides by 4 to isolate, and we get x is equal to 8.75 for the win. Done. Last but not least, there is a formula that is very important to know because they've been testing a lot on the digital SAT for this formula without providing it. And the formula is simply D is equal to M over V, where D stands for density and M is the mass and V is the volume. So sometimes they will give you the mass and the density and they'll ask you to solve for the volume, or density and volume and ask you to solve for the mass. So it's important to know this formula and write it down. Next, we're into unit conversions. Let's talk about conversion ratio. So we're going to take this example, convert 2 miles to feet. So we're going to begin with 2 miles. I'm going to throw it over 1 just to have a denominator. Now we need to convert it from miles to feet. So we need a conversion ratio, meaning an equivalency between miles and feet. Now, since I have miles on top over here and I need to convert to feet, I'm going to place miles on the bottom and feet on the top, and then we need an equivalency. Well, I know that 5,280 feet is equivalent to 1 mile, so that's all good. Now we're going to simplify by the units. I see miles on the top and the bottom. I can cancel them out. And now we're going to be left with an answer in feet. Then we just carry out the multiplication. 2 times 5,280 is 10,560 feet. That's how you use a conversion ratio to convert units. Here's another example. We're trying to convert 3 days to minutes. Now, you may not know how many minutes are in a day, but you can kind of do this step by step. So again, we're going to start with that initial value of 3 days. And first, we're going to convert it to hours because I know how many hours are in a day. That's a little bit easier. We know we have 24 hours to 1 day, right? And notice I have days on top on the left, so we need days on the bottom on that conversion ratio. Next, we're going to go from hours to minutes, and again, days are going to cancel out. So we know we're now in hours. Now I need a ratio, conversion ratio between hours and minutes. How many minutes are in 1 hour? 60 minutes in 1 hour. And again, the hours cancels out. Now we just carry out the multiplication on top. 3 times 24 times 60. It's all going to be over 1 times 1 times 1, which is 1. So multiplying on top, we get 4,320 minutes. Done. Now we're going to talk about square or cubic units. So this is actually pretty important. So for example, if we know the conversion between 2 units of length, we can use this to then go from, okay, well, I know how many feet are in a mile, but what about converting square feet to square miles? So this is how we're going to look at it. So check this out. Let's say I'm trying to convert 2 square feet to square inches, right? So you might be like, oh, well, there's 12 inches in a foot, so 2 square feet is just 24 square inches, but that's actually incorrect. So I'm going to show you why. So we know that 1 foot is equal to 12 inches. So if I know the length conversion, I can get the area conversion by squaring both of these 2 values. So again, we're going from feet to feet squared, so it kind of makes sense. We're squaring the actual values. So 1 squared is 1, but 12 squared is 144, which means 1 square foot is equal to 144 square inches. Therefore, 2 square feet is equal to 288 square inches. Now we're going to take an example where we're going to convert to cubic units. So again, we're going to convert 3 cubic meters to cubic decimeters. So first of all, what's the equivalency in length? We know that 1 meter is equivalent to 10 decimeters. So when we went to area, we squared these values. When we're going to volume, we're going to cube them. So 1 cubed is 1, but 10 cubed is 1,000. So now we have our equivalency in volume, right? So which means 3 meters cubed is 3 decimeters cubed. Now we're going to talk about percentages. And remember, what is the word percent? What's the derivation? It is a French word. It means per 100. Cent means 100 in French. So per 100. So 9% is literally 9 per 100 or 9 out of 100. Likewise, this can be represented in its decimal form as 0.09. Okay, 73%, again, 73 per 100 or out of 100. As a decimal would be 0.73. 16%, again, 16 out of 100 or 0.16. And last but not least, 125%, 125 out of 100, which simplifies to a decimal equivalent of 1.25. Next, we're going to talk about the percent equation to solve for percentages, okay? The percent equation is as follows. X% times the total is equal to the part. And again, in this case, my percent needs to be represented in its decimal form. And that's kind of the theme of percents when they're put into an equation. We're not taking like 30% of something, we're multiplying by 30. No, we're multiplying by 0.3, which is the decimal equivalent of 30%. So for example, here, if we say, what is 12% of 50, where 50 is the total? We're going to take 12, but we're going to move the decimal over 2 times, and we get 0.12. So we're taking 0.12 times the total, which is 50, is going to equal the part. And 0.12 times 50 is 6. Boom, done. Now we have another example. 9 is what percent of 45? So now we have to look back at the percent equation. And what do we have? We have the part, we have the total or the whole. We're trying to get the percent. So let's plug and chug. So we see we've got X percent times 45 is equal to 9. To isolate X, we're going to divide both sides by 45. And we get X is equal to 9 over 45, which is 0.2, okay? Now to convert this back into the percent, this is the decimal form of the percent. We move the decimal place over 2 spots, and we get our answer of 20%. Boom, done. Now here's the last possibility for a percent problem where we're now asking for what is the total, right? So we say 0.75, the decimal equivalent of 75%, times our total, whatever that is equal to the part, which is 30. To solve this, we're going to divide both sides by 0.75. 30 divided by 0.75 is going to be 40 for the win. Done. Now, what happens if they're talking about some sort of a percent increase, right? So let's say we have a starting value of 1,200 and we're trying to get a 20% increase. What that means is we're taking 20% and we're adding it to our 100%, and meaning we're ending up with 120% of the original value. So now we take that 120%, convert it into its decimal form, right, which is 1.2, and now we're going to take that 1.2 and multiply it by 1,200. 1.2 times 1,200 gives us our final answer of 1440. Remember, another way you can do this if we're increasing by 20%, you can also just take 20% of 1,200, which is 240, and add it back to the original. So those are two different ways to get to that answer. Now, if we're talking about a percent decrease, okay, let's say we're at 1,200 again, and we're doing a 35% decrease. Once again, you can take 35% of 1,200 and subtract that from 1,200. But the way that I like better is say, all right, well, it's a 35% decrease. So we're starting at 100% and we're removing 35%, which is the same as taking 65% of 1,200. So 65% of 1,200, we take the decimal point, move it over twice. And now we're going to do 0.65 times 1,200, which gives us an answer of 780. Next, I want to talk about this language distinction of percentage increase versus percent of, okay? And they love to test this specific concept on the SAT all the time. So let's talk about this. First, we have 120% of 50 versus 120% increase of 50. So it can get especially tricky when we're taking a percentage that's over 100%. That's when a lot of times people can get confused. But let me explain to you the gist of it. If you see this word of, we're taking 120% of, it's literally the decimal equivalent 1.2 times 50. Of is almost synonymous with multiplication. 1.2 times 50 is 60, and that's how you do it. Now, when they say 120% increase of 50, it means we take that percentage of 50, 120% of 50, and then we add it onto 50. It's an increase of 50. So one way to think about this is we're doing 120% of this added back onto the original amount. Another way to think about it is you can just add 100% onto this or take 220% of 50. But either way, that is 60 plus 50, which is 110, and that's the distinction in the language. So remember, if you see a percent of, you just straight up multiply. If you see 120% or a percent increase of, you take that percentage and you add it back on to the original value. Next, we're on to center, spread, and shape of distribution. So here's a data set, and I'm going to use this to explain mean, median, mode, and range. So first of all, let's talk about mean. When we're taking mean, we are going to add all these values up and divide by the number of terms. There are actually 13 terms here. Now, just FYI, in Desmos, which I've explained in my Desmos hacks video, you can literally type the word mean, parentheses, and then enter all the values with commas separating the values, and it will do the calculation for you. Next, in this case, that would be 5, right? Adding those up, dividing by 13, because there's 13 values, we get 5. Next, we're going to talk about mode. Mode rhymes with most. So think about the value that you see the most frequently, and in this case, we see 3 3s. So 3 would be the mode. We're talking about median. Once we have this data set arranged from least to greatest, it is that middle value. So the middle value here is 4. Now, when there's an odd number like here where there's 13, there's a nice, easy middle value of 4. When there's an even number, there's going to be 2 values in the middle, right? So let's say we have 10 values. The 5th value and the 6th value are going to be in the middle. And in that case, to get the median, you take the average of those 2 middle values, the average of the 5th and the 6th value, meaning you add them and divide by 2. Last but not least, we have the range, which is the difference of the greatest and the smallest value, which is 9 and 1. 9 minus 1 is 8. Boom, done. Next, we're going to talk about standard deviation. Now, I haven't seen a ton of standard deviation on the digital SAT, but it is good to know just in case. And you're not going to have to calculate it, but it's not a bad idea to understand it. And this is how it works. It is the measure of the spread of data. So, for example, when we have 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, versus here we have 6s and 7s, we see that on the left, the data is more spread out, so hence it would have a larger standard deviation. Here, it's more tightly packed together, 6s and 7s, so that's a smaller standard deviation. And if we look at the graphs, you can see that's all spread out evenly. That's a bigger standard deviation versus here, the data is more packed together. Next, let's talk about box and whisker plots. These will show up on the SAT, and this is how you're going to read them. So it kind of looks like this little rectangle with these 2 tails, right? So what is everything here? So at the beginning, we have the 2 ends, right? The one on the left is going to be the minimum, and the one on the right, that is going to be the max value. So that's 2 and 10 in this case. Then we have this middle line, and this may not necessarily be in the exact middle, but wherever you see this line, remember that is the median. You might say, well, isn't that also the mean? No, and by the way, you cannot tell what the mean is from a box and whisker plot. It's not going to show up in the diagram, but the median will. Next, we have the end over here on the left in orange. That is the lower quartile. I don't think this will be tested on the SAT, but it's not a bad thing to know. Then the other end of the box is the upper quartile, okay? And in this case, it is 8. And then we have the difference between the min and the max, which is, of course, the range, which we did talk about in a previous slide, but that's how it's represented on the box and whisker. And then last but not least, the difference of the upper and lower quartile, in this case is 8 and 4. That is called the interquartile range, or IQR for short, which in this case, once again, is 4. Next, we're going to talk about data representations, remembering that slope is rate, okay? And when slope is positive, that represents an increasing rate. Okay, and when slope is negative, that is a decreasing rate. And again, that's what slope looks like when it's negative going down from left to right. When we have a graph like this, the y-intercept is always our initial value, and on the graphs, that is where it hits the y-axis, which you can see on those 2 green dots. And then in the graph, if we see our x-intercept, that's going to show the point of no value, which you can see on these purple dots. Okay, so that's the point, the x value at which the y is going to go to 0. Now we can also look at slope in a nonlinear function. So once again, increasing slope would be like this section, right? Again, it's not a constant slope, but it's still sloping upwards, and that's positive. If we look on the other side, this is, again, negative slope going down from left to right. Our y-intercept, we can see, once again, that initial value for this quadratic is right there at 5, and the x-intercept, we have 2 values, okay? We have one at 5, but we also have one at -1. And then we have one more interesting point for a quadratic, which is a vertex, and that is going to be our min or max point, depending on the quadratic, depending on whether it's opening up or down. But a lot of times, if they are going to give you a quadratic and say, hey, we need you to find the greatest possible value, you know you're looking for the vertex. And of course, that value is represented as the top value right there. Now, here's a slope question in a data representation problem, right? So we have Zane likes to go rock climbing. Its elevation relative to the peak of the mountain is shown for the final 350 seconds of his climb. Time in seconds is labeled T, as shown above. At what speed in meters per second did Zane climb? So when they're asking for speed or rate with that per word, right? We know once again that we are talking about slope. So they're talking about the slope of this line. To calculate slope, we can take the rise, which is 25, over the run, which is 350. So that means the speed in meters per second is 25 over 350. We can reduce this to 1 over 14, which could also be represented as a decimal. But anyways, in fraction form, the answer is 1 over 14, done. Now, this is another question that's asking about the x-intercept. So check this out. The graph in the xp plane represents a relationship between the number of pairs of genes X that the manager in the department stocks for the season, and their profit, P, in dollars. What is the best interpretation of the x-intercept marked on the graph? So that's where it's hitting the x-axis. So again, as we mentioned before, the x-intercept is the point of no value for the y, in this case, the P, right? The P-axis, or the profit. So I should see something about getting a profit of 0, and that answer choice is going to be found in D, right? So once again, we're looking for x-intercepts, which are right here in purple. And what we're looking for in the answer choices is something that references a profit of 0. And where I see that is option D, because even though they don't say 0, they say breaks even. And we know that term of like no profit, right? Your costs are equaling your revenue. So you don't lose anything and you don't gain anything. That's what breaking even is. And those 2 points are given, right? 300 pairs of jeans or 900 pairs of jeans. That's how you do it. Now we have a y-intercept question. It says the graph in the AW plane gives Aiden's approximate weight in pounds at an altitude of 8 miles above the surface of Mars. Approximately how many pounds would Aiden weigh on the surface of Mars? So when we're saying on the surface, that means 0 miles above the surface. Hence, we're talking about the y-intercept, which is right there. So approximately, that looks in between 55 and 60, but closer to 55. So we're going to go with 57. So 57 pounds, done. Next, we're on to Scatterplots and in particular line of best fit. So check this out. An insurance company profits by collecting premiums at the beginning of each month, but pays claims over the remainder of the month. The scatter plot of the profit in millions of dollars on certain days since May 1 is shown on the graph at the left along with the trend line. Which of the following statements is true regarding the trend line? So let's check this out. And we've got this nice trend line coming down. I can see it's got a negative slope. So it says the profit by the end of May will be $2 million. And the reason why, even though it looks like that is the case, I don't know if we can say from the line of best fit that is a definitive statement. This is, again, an estimate, and that sounds very definitive. Let's go to option C. The profit decreases by approximately 1 million every 0.2 days. This sounds like it's trying to describe the slope. So let's check this out. Going down by 1 million every 0.2 days. I don't know. I disagree with that. It looks like it went down 1 million after 5 days. So I'm gonna disagree with option C. Option D, the profit is expected to decrease by $8 million over the course of May. It doesn't exactly look like that. And it does say expected, which I like, but it looks like it's only expected to drop by 6 million. So I'm going to discard D. But what about option B? The profit decreases by 1 million every 5 days. That's what we see here, right? It goes down by 1 over 5 days, right? In between 4 and 6. So that's how you do it. Done. Now, another thing you might have to do for a line of best fit problem is draw in a line or kind of imagine a line, and it could also be linear or nonlinear as well. So here's an example of a scatter plot, and the question is, is our line of best fit going to be linear or nonlinear? Because what we see here are 2 options on top that are linear and then 2 that are exponential. And as I kind of draw in this line, we see that it definitely should be curved. So I'm going to remove A and B as viable options. Now, usually an exponential like this is going to go up to the right, especially because this value right here is greater than 1. So since it seems like it's going down to the right, I'm going to go with option C. But let's verify that, right? Now we can do a little plug and chug and check. If I plug in 1 for R, and that is the round down here, I get 0.5 to the 1, which is 0.5 times 128 is 64. That matches up. What about 2? 0.5 squared is 0.25. 0.25 times 128 is 32. So we just confirmed with 2 points. That's really solid. So therefore, C is definitely the answer. Boom, done. Next, let's talk about how we distinguish between linear and exponential growth. So let's check out this table here of linear growth. And the way that we know it's linear is that X goes up by 1 every time, and the change in Y is consistent, meaning every time we're going up by 3, by 3, by 3, by 3, and so on and so forth. And again, this hinges on the fact that the X is going up as well by the same amount every time on the left-hand side. Now compare that with exponential. X's are going up by 1, by 1, by 1, but look at the Y's. Now it's going up by a factor of 2, meaning it's multiplying by 2, it's doubling. So when there's multiplication involved like this, it could even be 1.1 or 1.7, but if you're multiplying by a value, now we're talking exponential growth. So just to give you some examples, here's a nice linear equation. That's what a line would look like. Here's another linear equation with negative slope compared to exponential. Again, there the factor is 1.2 and it's going up. Now here it's between 0 and 1, and that's where we get this negative slope of of an exponential graph. Now we're moving on to probability and relative frequency. So first, let's talk about this table here, right? We have this table of males and females taking math and science. So a question they might ask is, what fraction of students surveyed take math? So to solve this question, right, we're looking at the total number of students, which is 270 plus 130. And on top is the amount of students that are taking math, which is 70. So as we simplify this, this reduces to 70 over 200 or 7 over 20. That's how you do it. Now we're taking the same table, but now we're asking a slightly different question. Of the females surveyed, what fraction of students surveyed take science? So now we're starting off with some conditional probability of the females surveyed. So we only care about the row with females. So females would be this middle row. So we're looking at that and we're saying, oh, there's 58 that take science out of the total females. Again, discarding the males now. So the total females is 46 plus 58. That is the conditional probability. And so we end up with 58 out of 104. Now, again, we have another conditional probability here. Of the students who like math, what fraction of students surveyed are male? So again, we're talking about math and we're looking at this column in math only. And it says, of the students who like math, which is a total of 70, what fraction are male? That's 24. So the answer is 24 over 70. Done. Now here we have a great sample problem. Let's take a look. So it says a manufacturer of plastics and epoxy resins has committed to eliminating the chemical BPA from its entire product line. According to the table, what percent of the manufacturer's products are polycarbonate products that contain BPA? So we want both polycarbonate and contains BPA. So we're looking at the intersection of that column and that row, which is going to be right there at 258. And now we're taking 258 out of the total, out of everything, which is 499. So we do the calculation, 258 divided by 499, we'll get the decimal equivalent of the percent, multiply by 100, and we get 51.7%. Boom, done. Now we're coming to data inferences, and it's very important for data inferences to read the graphs very, very carefully as well as the question prompt. So first, let's talk about margin of error. This is a big category for data inferences in particular. So margin of error, let's say we get an example where they say, hey, we think the sample mean is 72 with a margin of error of 5. So what does that mean? That means that it is highly likely that we have an actual sample mean of 72, in between 72 minus 5 and between 72 plus 5. So for example, we immediately know that a plausible value for the mean is somewhere between 67 and 77. It's very important to note that this doesn't mean definitively that the mean is within that range of 67 to 77, but it's highly plausible that it's within that range. Now let's take a look at an example problem. It says a random sample of 34 four-door passenger vehicles had a mean gas mileage of 25.9, and there's a margin of error of 2.6. Now that confidence level, they haven't really tested at all on confidence level on the new SAT, so I would not worry about that for the time being. But how do we use that margin of error? So once again, we have a mean of 25.9 and a margin of error of 2.6. That tells me that a plausible value, which is what they're asking, right? Most plausible value for the true mean is going to be between 25.9 minus 2.6 and 25.9 plus 2.6. That means a plausible value will be between 23.3 and 28.5. And the only value that fits in that zone is 24, which is A. Done. Now we get another problem here in data inferences. It says 40 randomly selected Crowhaven Community College students were asked about their preferred way of getting to class. The bar graph shows the results of the survey. If 6,000 students attended Crowhaven Community College, which of the following best approximates the number of students who prefer walking to class? So let's check this out. So again, we're looking at the best approximation of students walking to class, and we see we've got 18 students walking to class, and that's 18 out of 40 surveyed. That means the fraction of students, according to the survey, is 18 out of 40. Now, to get the total number of students that prefer walking to class, we got to take this fraction of the total, which is 6,000. So we're going to do this multiplication, and we end up with 2,700 for the win. Done. Now we get another example problem. It says Bernard randomly selected 10% of St. Francis citizens and asked them about their favorite coffee shop. Of the citizens surveyed, 7 said that Energize was their favorite coffee shop. Based on the data, what is the most reasonable estimate of the number of citizens whose favorite coffee shop is Energize? So what I'm going to do here is I'm going to set up a proportion to solve this, and the proportion is going to be percent relative to the amount of people. So for example, I see that 10% is equivalent to 7 people in the survey. So what I want to know now is what is going to be 100%, right? So if we expand this to the entire population, which is 100%, how many people are going to say Energize is their favorite? So now we got this great proportion. Let's cross multiply and solve. So we get 7 times 100, which is 700 equals 10x. Divide both sides by 10 to isolate x, and we get x is equal to 70, which means D is the winner. Done. Finally, we get to number 10, which is evaluating statistical claims. So let's check it out. It says apply findings to population sampled. All right, so let's dive into this. What does this mean? Let's read this example and let's talk it out. So Sweet Treats Candy Company wants to introduce a new flavor of jelly bean. They have 3 choices. They decide to do a survey to determine which flavor their customers prefer. All customers at their store tried a free sample of all 3 flavors for a 2-week period. 55% preferred mango, 20% papaya, and 25% preferred coconut. Based on this data, which of the following conclusions is valid? So first of all, who did we survey? We surveyed all customers at the store, okay? So that means that when we're trying to apply the results of the survey, we can only apply it to the population that was sampled, which is all customers. So now we look at option A. Is it logical to apply this to the entire world? I think not, right? Again, we have 55% of all jelly bean eaters. That's a bit of a leap. Then we come to D. People who prefer papaya are probably allergic to mango. There is nothing said about allergies. This is almost kind of a funny option. But what about C, right? 55% of all customers who shopped at Sweet Treats, because that's the population that we were sampling, 55% of all customers who shopped at Sweet Treats store during the sampling period prefer mango. That is a reasonable conclusion. We can apply that logically. That makes sense. Done. Now, when we talk about data collection, the thing we want to look out for on the digital SAT for problems with data collection in particular is we want to look for inherent biases in sampling. We can get biases from the location where we perform the sample. We can get biases from location where we take the sample. We can also get it if we are leaning towards certain preferences. So for example, this one, school district wants to conduct a sample survey to determine the average number of sports played by high school seniors. So we're looking at the survey methods and which ones are likely to produce valid results. Well, if I look at A, they're selecting high school seniors who play baseball, but we're automatically going into preferences of people who like baseball, where they're probably going to be more likely to play sports. So that's a bias that we don't want. We want this to be a random sample, but not a random sample of people who are already athletes. We also have B, which has a location preference. We're taking every 10th student to enter the football stadium. So again, there's going to be a greater likelihood if you're going to a football stadium that you're going to like sports. So that biases the results as well. Finally, option D is a bias because we're taking one high school in the district and surveying all their students. It's not so bad, but if we really want to get a representation of the district, we should go with option C, where we survey 500 randomly selected high school seniors in the district. Now for this one, it says near the end of a local radio talk show, the host invited listeners to respond to a poll on the show's website that asked, are you in favor of the city's new restrictions on the types of flags homes can fly? At the end of the show, the host reported that 22% responded yes and 72% responded no. So now we want to talk about what is the potential bias. So think about it. This is a local radio talk show, and a lot of these talk shows might have political leanings one way or the other, meaning that audience that's tuning in is already going to have inherent biases, and that's why they're tuning into this show. Now, they don't say that explicitly, but what we can say is that this is definitely not a random sample because, right, they're going on the show's website. So I would go with option D. It's just simply not a random sample, and that's how you do it. Done. So that's it for problem solving and data analysis. Now we're going to move on to advanced math. Now we're moving on to part 3 of 4, advanced math. Let's go. So for advanced math, we have the following subcategories, and we're going to go through each and every one. So we have factoring quadratic and polynomial expressions, radical and rational exponents, operations with polynomials, operations with rational expressions, nonlinear functions, isolating quantities, solving quadratic equations, linear and quadratic systems, radical, rational, and absolute value equations, quadratic and exponential word problems, quadratic graphs, and exponential graphs, and finally, polynomial and other nonlinear graphs. So as we start with factoring quadratic and polynomial expressions, it's important to know what is factoring. So let's say we have an expression like this. One way that we could factor an expression like this just by simply taking out a GCF is by dividing every one of these terms by 2. So you pull a 2 out, and then the resulting polynomial is x squared plus 2x plus 4. Another way is factoring out a variable, right? We can factor out x here as the GCF, And then we can also have our typical example of a quadratic, which we're going to go over in a later slide for the specifics, but this one you can factor into 2 binomials. And then of course we could have something like this with 4 terms, and we could factor it as follows. So first we're going to talk about factoring quadratic. So we have a typical quadratic right here, x squared plus 5x minus 6. Now, the way that we factor this, especially since there is no leading coefficient in front of the x squared, it's as follows. We figure out what numbers multiply to -6 and adds to +5, right? And so those two numbers are +6 and -1, and it factors as x plus 6 times x minus 1. Now, the reason why we know this is correct is because if we redistribute, meaning if we FOIL these two binomials, we'll come back to the original trinomial. So let me show you what that looks like, right? So we're going to carry out FOILing, which is we multiply the first two terms, x times x, which is x squared, and then we multiply the outer terms, that's the O, so x times -1 is -x. Then the inner terms, that's the I, 6 times x is 6x. And then the last term, 6 times -1, which is -6. Then we're going to combine like terms, and -x plus 6x is 5x minus 6. And you see that we return back to the original trinomial. That means that the way we factored it here was indeed correct. Now, let's say we have a quadratic with a leading coefficient. Now we're going to have to factor using something called the star method. So the star method would come into play here because we have an 8 for that leading coefficient. So the way we carry out the star method is as follows. We draw this star, and A, B, and C are placed into this diagram as follows, right? So you look at that color coding. That's A, that's B, that's C. So check it out. On the left and right, we're going to put the 8. On the bottom, we're going to put that B term, which is 2. And up here, we've got A times C, which is 8 times -3, which is -24. Now we ask the question, what two numbers multiply to that -24, but also add to 2? So the answer to that, right, so you can see here, right, we're multiplying to A times C and adding to B. So the two numbers that would fit that bill are going to be -4 and 6, right? You add them together, you get 2, you multiply them, you get -24. Then you're going to treat these like fractions. 8 over -4, how can you reduce that? You can reduce it to 2 over -1. What about 8 over 6? You can reduce it to 4 over 3. Now these numbers are going to form the coefficients and constants of the factored binomial. So for example, the first one is going to be 2x minus 1. Notice that the top number goes with the x, the bottom one is a standalone constant. And the second one is 4x plus 3. And that is how you get your final factored form. Next, we're going to talk about sum of cubes. Now, these don't normally show up on the digital SAT, but I'm giving them just in case they do pop up, so I want to take you through this process. So let's say we have a sum of cubes, which is x cubed plus b cubed. These are both perfect cubes, right? To factor a sum of cubes like this, we use a rule called same, different, plus. That tells us the layout of the signs. And you're going to see why that helps as well when we're talking about difference of cubes. Same meaning we have a plus here. Different meaning if we had a plus here, we have a minus. And plus means we always end in plus. And then the breakdown is whatever we have in the first spot, that's going to go here. But the cube root of that, whatever is going to go in the second spot, we put that cube root right here. And then over here, we have the first term squared. Over here, we have the product of these guys. And over here, we have the square of the last term. So for example, if we have x cubed plus 27, it's going to be x plus the cube root of 27, which is 3. And then the first term squared, the product of x and 3 right here, and then the last term squared 9. Now, if we have a difference of cubes, right, we have x cubed minus b cubed. Again, same, because the minus, different than the minus is plus, and then plus at the end, same, different, plus. And then it's the exact same layout. And now we'll do another example here. 8x cubed minus 27. Again, the cube root of 8x cubed is 2x. The cube root of 27 is 3. We have 2 squared here, which is 4. 2 times 3, which is 6 here, and 3 squared, which is 9 here. Now we're into radicals and rational exponents. First of all, let's talk about square root. So a square root is asking what number times itself gives us the value under the square root. So of course, the square root of 1 is 1, because 1 times 1 is 1. Square root of 4 is 2, and so on and so forth. Now these are all perfect squares. When we're taking the square root of variables, right, we can take the square root of x squared. The square root of that is x, because x times x is x squared. Likewise, with to the 4th power for other even values, it's almost like you're dividing by 2, right? The square root of x to the fourth is x squared, x to the sixth is x cubed, so on and so forth. Now, if we talk about a cubic root, that is asking what number times itself, then times itself again equals the original number. So again, the cube root of 1 is still 1. The cube root of 8 is 2. Now, you might say, why didn't you include the cube root of 7 or 6? Those are not perfect cubes. So you can say, what is the cube root of 7? It's some decimal approximation, but there's no exact cube root. So we also have cube root of 27, which is 3, cube root of 64, which is 4, cube root of 125, which is 5, just to give you a couple examples. We're talking about variables. Again, we can take a cube root of variables that are raised to a multiple of 3, right? So the cube root of x cubed is x, because x times x times x is x cubed. Cube root of x to the 6 is x squared, and so on and so forth. Now, when it comes to simplifying roots, okay, we can take an example of a square root. So when we're taking a square root, right, we don't necessarily have all perfect squares inside. So we can't simplify everything and just take the square root of everything. But what we're going to do is we're going to look for perfect squares within each number and variable. So for example, I see 32. I know that 32 is really 2 times 16. 16 is a perfect square. X cubed, we have x times x squared. X squared is a perfect square. Y to the 6th is a perfect square because it's an even exponent. And then z to the 9th, we've got z times z to the 8th, which is another perfect square. And notice, I'm trying to find the largest perfect squares that I can pull out of each of these. So now for all these colored numbers and variables, we're not going to take the square root, okay? So the square root of 16 is 4. That comes out of the square root. Square root of x squared is x. That comes out. Square root of y to the 6th is y cubed. Again, we're taking half. And remember, y cubed times y cubed is, of course, y to the 6th. And then the square root of z to the 8th is z to the 4th. Now, what's left inside? The 2, the x, and the z. Those cannot come out, and it cannot be further simplified. So this is how you simplify a radical. Now, let's say we're talking about a cubic root, okay? So now I've got a similar expression. We're taking a cubic root of this expression. We need to extract the perfect cubes. So I'm going to rewrite 81 as 3 times 27. 27 is a perfect cube. We've got x times x cubed. Y to the 6th is a perfect cube because, again, 6 is a multiple of 3. And then we're taking z to the 11th. We're breaking it up into z squared and z to the 9th. Now let's take the cubic root of 27, which is 3. 3 times 3 times 3 is 27. Cubic root of x cubed, we're basically dividing by 3. It's x to the 1st. Cubic root of y to the 6th is y squared. Cubic root of z to the 9th is z cubed. And then everything else stays inside. That's how you do it. Done. Now, what about when you have a radical in a denominator? You're going to need to rationalize that denominator. So what are we talking about here? So let's say we have 3 over rad 5. Now, a lot of times on the SAT, they're not going to have this as an answer, right? A number over a radical. They're usually going to present it with the denominator being rationalized, meaning you've removed the radical. So the way we remove the radical is as follows. If I have 3 over rad 5, I multiply by rad 5 over rad 5, right? Because rad 5 over rad 5 is 1, so that's legal. I can multiply anything by 1. It's still itself. I haven't changed the value. But the reason why this is great for rationalizing the denominator is rad 5 times rad 5 is simply 5. So we have 5 now on the bottom, and on the top we have 3 rad 5. So this is the way to write it after we have rationalized the denominator. Now, let's say we have a radical like this, where it's 3 over 4 plus rad 5. We can't just multiply by rad 5 because we'll still have a rad 5 attached to the 4. We have to multiply by something called the conjugate. So the conjugate is the exact same thing, except you change the plus to a minus or vice versa. So here, the conjugate is 4 minus rad 5. Now, as we would multiply this out, remember, we're foiling, okay? So again, you'd say 4 times 4 is 16. 4 times negative rad 5 is minus 4 rad 5. We have 4 times positive rad 5, which is 4 rad 5. And then we have rad 5 times negative rad 5. Again, a radical times itself just becomes the number, and because of the negative, it's minus. Now look, these two in the middle cancel out because they're opposites. 16 minus 5 is 11. So now we have 16 minus 5 on the bottom, and on the top, we're just distributing the 3, and we've got 12 minus 3 rad 5. But what is important is we no longer have a radical in the denominator. So now we can simplify this to 12 minus 3 rad 5 over 11. Done. Next, we're going to talk about converting between radicals and rational exponents. So for example, if we have a rational exponent, 8 to the 2/3, what does that mean? Well, what that means is the numerator is the power we're raising this to. The denominator is the index of the root, okay? So this is saying we're really raising 8 to the second power and taking the cube root of that value. Or we could write it as the cube root of 8 and then squaring that value. So the order of those operations actually doesn't matter. You're going to get the same answer both ways. Now, the easier way is to do it on the right. Go small, then big, as opposed to big, then small. Because on the left, you'd say 8 squared first, which is 64, and then you take the cube root of that. On the right, you're saying, oh, what's the cube root of 8? It's 2, and then you're squaring 2. That's pretty easy. That's 4. But in either case, you're still going to get 4. So check it out. In this case, cube root of 64 is 4, as well as here we get 2 squared, which is also 4. Boom, done. Now let's do a quick recap of our rules for exponents when we multiply and divide. So first of all, when we multiply two variables, we are adding those exponents. So here we get x to the 11th. When we are dividing x to the 7th divided by x to the 4th, we are subtracting those exponents. So this would give us x cubed. Now just FYI, when we have variables with different exponents, we cannot add them. They must stay separated. Likewise with subtraction, they will not combine. So different exponents are almost like different variables. When we talk about negative exponents, what do negative exponents mean? Well, for example, if we have x to the negative 7th, that is equivalent to 1 over x to the 7th. But what about if we have a negative exponent in a denominator? What I like to say is if you have a negative exponent in the denominator, that variable is in the wrong position. Meaning, if it's negative in the denominator, it belongs on the numerator. If it's negative in the numerator, it belongs on the denominator. And once you move it, it becomes positive. So in this case, we would bring that x to the negative third up to the positive third. And I also divided 8 by 2, and that's how I got 4. Now we can combine x to the first times x cubed. We're adding those exponents, and we get 4x to the 4th for the final simplified expression. Now we're on to operations with polynomials. What is a polynomial? Well, you could have a binomial, a trinomial, and this has a 5-term polynomial. You could also have a monomial, which is just 1 term. A monomial example would be 3x to the 6th, and a binomial, again, 2 terms, would be 2x to the 4th plus 7. Now, it's not so important that you know the terminology. I'm just giving it to you so that you have a little bit of background information as we go forward with the operations. Now, first of all, let's talk about adding and subtracting polynomials. So this is a trinomial plus a trinomial. Now, when you're adding these two trinomials, the parentheses aren't really doing anything, so we can pretty much get rid of them. And then what we're going to do is we're going to combine like terms, meaning I'm going to combine the 3x squared and the 4x squared because they are both have the same degree, right? So 3x squared and 4x squared are going to be like terms. Likewise, negative 2x and x, those are going to be like terms. And finally, these constants at the end are going to be like terms. So we're going to combine them. 3x squared and 4x squared gives me 7x squared. Negative 2x and x gives me negative x when we add them together. And negative 5 plus 2 gives me negative 3. Now, when we subtract polynomials, we do have to pay attention to those parentheses because we're going to distribute that negative to the second trinomial. So now you see I flipped the sign of 4x squared of x and of 2. And once again, we're going to combine like terms. We got the x squared terms, we've got the x terms, and we got the constants at the end. 3x squared minus 4x squared is negative 1x squared or negative x squared. Negative 2x and negative x is negative 3x. And finally, negative 5 and negative 2 make negative 7. Now, what about multiplying two polynomials? So when we multiply them, we are going to distribute once again, but I'm going to show you the process for this. So we're going to start with this first term, 2x, and I'm going to distribute it to each and every term of the second trinomial. So first we're going to say 2x times 4x squared, which is 8x cubed, 2x times x, which is 2x squared, and 2x times 2, which is 4x. Now we're going to focus on the negative 5, and the negative 5 is going to go down the line, hitting every term in the second trinomial. So we got negative 5 times 4x squared, which is negative 20x squared. Negative 5 times x is negative 5x, and negative 5 times 2 is negative 10. Now we're going to combine like terms. I've got 2x squared and negative 20x squared gives us negative 18x squared. And then we got 4x minus 5x gives us that negative x. And that's how you multiply two polynomials. Now, if they ask about dividing polynomials, which has shown up a lot less on this new digital SAT, I want to show you the process and how to do this, just in case it shows up. Again, I don't anticipate a synthetic division or a long division for polynomials to show up on the digital SAT, but I just want to give you the process just in case. So Let's say we're dividing this large polynomial by x minus 1 or x minus 3 or x plus 4. The process is as follows, okay? You take the opposite of this value right here. So that's minus 1. So we're going to take 1 and we're going to throw it in a little box. And then we're going to take all these coefficients from the highest degree down and we're going to place them like so. 1, 4, negative 3, and 1. And then we're going to go as follows. We're going to drop that 1 and we're going to multiply it by the box number and place it underneath the next number, underneath the 4. Now we're going to add. We're going to say 4 plus 1 is 5. Then we're going to repeat. Again, 5 times 1 is 5. Place that underneath the negative 3. Add them together. 5 plus negative 3 is 2. Then we're going to do it again. 2 times 1 is 2. We're going to place it underneath the 1, add them together, and we got 3. So what have we just done? We've actually divided these polynomials, and now the resulting polynomial, once you carry out that division, is going to have the following coefficients that we see on the bottom here: 1, 5, 2, 3. And they're going to start with 1 degree less than the original left polynomial, which is x to the third. So we're going to start with 1x squared plus 5x plus 2, and this last value is the remainder, and that remainder is going to be placed over the original divisor of x minus 1, and that's how you carry out synthetic division of two polynomials. We can also divide via long division. So again, let's say we have this polynomial divided by this polynomial. We can carry it out with our standard long division algorithm. Now, long division is especially good when we have this leading coefficient, right? A 2x minus 1 or something else other than just a x plus 5 or x minus 3. So let's check it out. We're going to set it up as follows, and we're only paying attention to the big term and this term, right? We're trying to get 2x to go into 4x cubed initially. We're not worrying about that negative 1. So what times 2x gives me 4x cubed? I'm going to multiply it by 2x squared, right? So now we're going to multiply that entire binomial. 2x squared times this guy is 4x cubed minus 2x squared. Then we are going to negate, because it's like I'm subtracting the bottom, that bottom polynomial, just like in regular long division, right? So I just say negate instead. Then I add them together. You see that those cancel out, which they should. 4x squared plus 2x squared is 6x squared. Now I'm going to bring down the next term, and then we're going to repeat. What times 2x gives me that leading term 6x squared? That would be 3x, right? We multiply the entire binomial, so we get 6x squared, and then 3x times negative 1 is negative 3x. Now again, we're going to negate, because we're subtracting, right? And so now I've negated. Now we can just add 6x squared minus 6x squared, cancel out. Negative 8x plus 3x gives us negative 5x. Finally, we drop that last term, and we do it one more time. What times 2x gives me negative 5x? That would be negative 5 over 2. Then we're going to multiply it, and we get negative 5x plus 5 halves. Again, we're going to negate, and we're going to combine these. These guys cancel out. 1 plus negative 5 halves is negative 3 halves. Again, that's my remainder. And so my remainder goes up again over that original divisor, and everything else stays as is. So that's how you carry out polynomial long division. Next, we're going to talk about operations with rational expressions. So, how do we simplify rational expressions? First of all, what is a rational expression? A rational expression is something over something, pretty much. We can think about it like that on the SAT. Now, we've got this rational expression divided by this rational expression. Okay, if you're given something like this, first of all, we want to turn that division into multiplication using keep, change, flip, right? So we're going to keep the original term, change that division to multiplication, and flip this to 3x over 9x minus 15. Now we're going to do some factoring. Okay, so a thing that I like to say in the SAT is if you're not sure where to go, but you see something that's not factored and can be factored, just factor it and see where it goes. That might give you an idea of what steps to carry out next. So we can factor this top polynomial into 3x minus 5 times x plus 1 using the star method. On the bottom, we've got a GCF of x, so I'm going to factor that out here. Over here on the right-hand side, we can just factor out a 3 on the denominator. So we have 3 times 3x minus 5. Now we can simplify. So since everything is being multiplied, if I see the same polynomial or term on the top and the bottom, I can cancel them out, right? Because anything over itself is 1. So 3x minus 5 over 3x minus 5, gone. X plus 1 and x plus 1, gone. X and x, gone. And also 3 and 3 are gone. Well, if everything cancels out, that means the top and the bottom were exactly identical, meaning we're ending up with 1. Now, what about when we're trying to simplify the difference or sum of two rational expressions? Well, in this case, if they don't have common denominators, we cannot combine them, but we're going to need to, because a lot of times on the SAT, that's what they want. When they're showing you a rational expression minus another rational expression, they're going to say, what is it equivalent to? And they're going to give you answers, hoping that you're going to consolidate these by getting a common denominator. So let me show you how we're going to do that. So we have two totally different denominators. The only way we're going to get common denominators is I'm going to multiply the left term by the right denominator over itself, and then the right term by the left denominator over itself. Again, I can do this because anything over itself is 1. So I'm not really changing the value of these expressions. I'm just reformatting them so we can kind of merge everything together. So now on the bottom, we've got 3x minus 5 times x plus 7. I'm not going to combine that. I'm going to leave it in factored form. But on the top, I'm going to distribute the 3. And we got 3x plus 21. Over here, I'm going to distribute that negative 5. We got negative 15x plus 25, right? The negatives are going to cancel out. Once again, leaving this down here. And then we're going to combine like terms. 3x minus 15x is negative 12x. 21 plus 25 is 46. And oftentimes, again, for digital SAT problems, you're going to see the correct answer looking just like this. Next, let's move on to nonlinear functions. And nonlinear functions are just anything where x is going to have an exponent greater than 1, right? Like this is a cubic function, or you could have a quadratic raised to the second power, so on and so forth. So here we've got 3 different nonlinear functions. Now, one of the things you're going to have to do with these function questions is understand function notation. For example, you might see f of 2, g of 2, or h of negative 2, and you have to evaluate these expressions. Okay, so what is this really asking? You'll notice that the 2 is in the position of the x. So what they want you to do here is to find f of 2, you're going to plug 2 in for x. So we've got 3 times 2 to the third power plus 7. 2 to the third power is 8. 8 times 3 is 24. 24 plus 7 is 31. Okay, so that's how you'd find f of 2. G of 2, you're going to plug 2 in for x in g of x. So we have 5 times 2 to the fourth. 2 to the fourth is 16. 16 times 5 is 80. That's how you do it. Last but not least, negative 2 into h. That would be negative 2 squared, right? Plus 3. Negative 2 squared is 4 plus 3 is 7. That's how you do it. Now, another version of a nonlinear function question could be if f of x is 31, find x. So now they're telling you that the function value is 31, and you need to find what value of x gives us that function value. The way I'd evaluate this is I replace the f of x with 31 and set it equal to 3x cubed plus 7. All right, now let's simplify. So we're going to minus 7 on both sides. Boom, boom. 31 minus 7 is 24. 24 equals 3x cubed. Then we're going to divide both sides by 3 like so. Boom. And we got 24 divided by 3 is 8 equals x cubed. Last but not least, we need to take the cubic root of both sides, right? Then we just have x. What is the cubic root of 8? What number times itself, then times itself again, is 8? That would be 2. X equals 2 for the win. Done. Now we're going to look at a couple other function operations. We're going to look at f of 1 plus g of 3. We're also going to look at g times h of negative 1 and function composition here, h of g of negative 2. Okay, so f of 1 plus g of 3, that means we're meant to find f of 1, we're meant to find g of 3, and then simply add them together. F of 1, we'd plug in 1 here. 3 times 1 to the third is 3, plus 7 is 10. And then what about g of 3? 3 to the fourth is actually 3 times 3 times 3 times 3, which is 81, times 5 is 405. Then we're going to add these together, and we get 415. What about g times h of negative 1? What this is really saying is we're going to find g of negative 1, and we're going to find h of negative 1, and then we're going to multiply those two together. G of negative 1, if you plug in negative 1 here, negative 1 to the fourth is 1 times 5 is 5. H of negative 1, plug in negative 1 here, negative 1 squared is 1 plus 3 is 4. 5 times 4 is 20. That's how you do it. Last but not least, we got this one. Now, this might look like we're multiplying, but it's a little bit different operation when it's hollow like that. This is really saying what is h of g of negative 2. So what this means is we're first finding the inside, which is g of -2. Whatever that value is, then we're plugging that in for h, right? So first let's find g of -2. Plug in -2 here. -2 to the fourth is -16 times 5 is -80. So I'm going to replace g of -2 with a -80. Now we're plugging in -80 into h of x, right? So we've got -80 squared plus 3. -80 squared is 6,400 plus 3 is 6,403. That's how you do it. Done. We also want to talk about transformations, especially in function notation, which definitely shows up on the digital SAT. So when you see something like this, we got a function f, and they're saying we're now doing f of x minus 2. This is a shift of 2 units to the right. I know it looks like you might think, hey, it's 2 units to the left because it's minus, but it's actually the opposite. We're talking about x minus 2 or x plus 2 within the parentheses. So likewise, f of x plus 7 is going to be going 7 to the left, okay? Now, what about if we have f of x and then outside of the parentheses minus 2? This is going to be a vertical transformation. This one in particular is going to be transforming it or translating it 2 units down. F of x plus 7, again, is going to be 7 units up. So when it's outside, it's sort of more intuitive. Minus is down, plus is up. When it's inside the parentheses, minus is to the right, plus is to the left. Now I want to show some nonlinear functions in factored form, and when we put them in factored form, the reason why this is important is because it allows us to find the zeros of the function. So we can look at each individual piece, like the x and the x plus 2 separately, and say, all right, what's going to send x to 0 and what's going to send x plus 2 to 0? To send x to 0, it's simply 0, and to send x plus 2 to 0, we need a -2 because -2 plus 2 is 0. What about g of x in this expression? Well, if we factor it to x plus 2 and x plus 5, what's going to zero each of those out, each of those binomials out, is going to be the opposite of 2 and 5, which is -2 and -5. Finally, when we have this one where it's factored into 3 binomials, we look at each of them, right? We've got 3 here, 2 here, and then what's going to make this one go to 0? What times 4 minus 1 is going to give me 0? 1/4, right? 1/4 times 4 is 1, minus 1 is 0. So those would be your 3 zeros right there. And again, these zeros are another way of saying x-intercepts. Next, we're on to isolating quantities. When you get an isolating quantities question, you're going to want to isolate a particular variable. You'll be able to see which variable they want you to isolate either in the prompt or by looking at all the answers, right? They're going to have the same variable isolated. So you're going to start with some sort of a formula. So here we've got a is equal to 1 plus x over 2x. And now we're going to try and get x by itself. So I gave a particularly hard example where we have that variable that we want to isolate both in the numerator and the denominator. So let me show you how we're going to do this. First, we're going to multiply out that denominator. Let's start there. So we have 2xa equals 1 plus x. Now I need to get the variables on the same side, meaning x on the other side as well. So we're going to minus that x. Now we have 2xa minus x equals 1. In this case, the only way to extract the x is we're going to have to factor it out of both of those terms. So we're going to factor it out, and we're left with 2a minus 1. Last step, we divide by that entire binomial of 2a minus 1 on both sides, and we're left with x is equal to 1 over 2a minus 1. That's what you're going to have to look for in the answer choices on an isolating quantities question. Next, we're on to solving quadratic equations. So again, when we're solving quadratic equations, we got a few different methods that we can utilize. The most common and the most popular by hand is factoring, okay? So let's say we have this quadratic equation set to 0. And by the way, if it's not set to 0, you want to get it set equal to 0. And then we're going to factor, as we showed before, we're going to say what multiplies to -6 and +5, and that is +6 and -1. But the key is once we have it in factored form, we can solve this, right? Because we're setting this equal to 0, so we need to know what's going to make this binomial go to 0, or what makes this binomial go to 0. Because if either of them go to 0, 0 times anything is 0. So the answers are going to be -6, +1, boom, done. Another option is completing the square if you're doing this by hand. And if you're a fan of this method, great. If not, again, you have other tools in your toolkit. So completing the square, let's say we have this quadratic right here. To complete the square, the first step is we're going to move that 8 over. We're going to minus 8 from both sides. Then we're going to take that -6. We're going to divide it by 2, which is -3, and we're going to square it. -3 squared is 9. We're going to take that value and we're going to add that to both sides. So 3 squared, which is 9, to both sides, okay? Then what we're going to do on the right-hand side, -8 plus 9 is simply 1. But on the left-hand side, we're going to factor it. And you might say, once again, all right, what two numbers multiply to 9 and add to -6? It's -3 and -3. And the fact that it's the same number times itself, that's by design. We've created a perfect square. So this factors to x minus 3 times x minus 3, which is x minus 3 squared. Okay, and again, we have 1 on the right-hand side. Now we're going to take the square root of both sides, right? So I can take the square root of x minus 3 squared, which is just x minus 3, and the square root of 1, which is plus or minus 1. Hence, we have two equations, right? X minus 3 equals -1, x minus 3 equals +1. Now we're going to solve. On the left-hand side, we're going to add 3 and we get x equals 2. On the right-hand side, we're going to add 3 and we get x equals 4. Those are our two solutions. Done. Another option we have is the quadratic formula. This is especially going to be useful if we have a solution for the quadratic that is not rational. So I'm going to give you an example here. We have 2x squared minus 4x minus 16 equals 0. The quadratic formula is as follows. -b plus or minus the square root of b squared minus 4ac all over 2a. You've got to have this memorized. Now, a, b, and c are those numbers that are color-coded in blue, red, and green. So as we plug in, we just plug in those values as follows, and we evaluate this expression. Underneath the radical, 4 squared minus 4 times 2 times -16 evaluates to 144. And then we still have the 4 out here, and 2 times 2, which is 4 on the bottom. Then we take the square root of 144, which is 12. 4 plus 12 divided by 4, and 4 minus 12 divided by 4. So we get +4 and -2 for the two solutions. Done. Now, just a quick reminder for those solutions that are not rational, you might have something that stays in the radical that doesn't have a perfect square. So you're going to have a radical in your final answer, but just wanted to give you that possibility. Is a lot of times when they want you to use the quadratic formula, it's because you're going to end up with a radical. The last way we can solve this is using Desmos, which is a really, really great way to solve these quadratic equations. So let's say we get something like this. Straight, nice, and easy. We just throw it into Desmos as is. And the two solutions will be shown as follows, like these two lines. And we're looking for the x values of these two lines. So for example, I've got -2 and 4 for my solutions, which the -2 comes from that coordinate and the +4 comes from that coordinate. Now, in case you get a quadratic and they say, hey, we want either the sum or the product of the solutions, we got a nice little shortcut. So coming back to the same equation where we know the solutions were -2 and 4. If we know the solutions, oh, what's the sum of the solutions? -2 plus 4. Great. What's the product? -2 times 4. But let's say we don't know the solutions. Let's say we haven't factored or we haven't used the quadratic formula, and we just want to get to the sum or the product. There's an amazing shortcut. And the reason why I'm providing this is because some of the questions are going to want you to use these formulas as a shortcut. So if they say, hey, what's the sum of the solutions? It's this nice little formula, -b over a, where -b is -4 over 2, right? So it's 4 over 2, which is 2. Again, that makes sense because the sum of -2 and 4 is indeed 2. What about product? The formula there is c over a. So in this case, that would be -16 over 2, which simplifies to -8. And again, we know that this is correct because -2 times 4 is -8. Now, if we get a question that says, what is the nature of the solutions, or how many solutions are there for this quadratic equation? We know we need to use the discriminant. So that's how we find the number of solutions, right? So let's say we have a quadratic equation like this. The discriminant is b squared minus 4ac. And again, it's just those numbers without the variables. So this is going to tell us whether we have 0, 1, or 2 solutions for a quadratic equation. And by the way, we can't have anything else. It's either going to be 0, 1, or 2. That's it. So when we have no real solution, meaning 0 solutions, this discriminant is going to be negative. So in this case, right, it's 9 minus 4 times 2 times 5, which is going to be -31. That's no real solutions. One real solution is when the discriminant is equal to 0, like in this example. And finally, 2 real solutions is simply when the discriminant is greater than 0. Next, we're on to linear and quadratic systems. This is going to be when you're given a quadratic and a linear and you're meant to solve it, meaning you're meant to find the intersection of these two functions. So you can see the graph of this quadratic in this line here. The solutions would be 0, 3 because that's where they intersect, as well as 4, -5. Now to solve the system algebraically, you can carry out the following steps. We can use substitution, right? So I see that y equals x squared minus 6x plus 3, I can substitute that in for the y over here, and we get this nice equation. Now we're going to set everything equal to 0. We're going to subtract 3 from both sides and add 2x to both sides, which is going to give us x squared minus 4x is equal to 0. Again, 3 and negative 3 are going to cancel out. Now to solve this quadratic equation, we're going to factor, right? We're going to pull out the GCF of x, and then we're going to say what makes x go to 0 and what makes x minus 4 go to 0. And that gives us our two solutions, 0 and 4. Now, to find the coordinates of where these intersect, you can now plug in these x values into either equation. I'm going to plug it into the bottom one because it's a little easier. So you plug in 0 here. 0 times negative 2 plus 3 is 3. 4 times negative 2 plus 3 is negative 5. So our final solutions are 0, 3, 4, negative 5, done. Now, of course, we also have the option to solve with Desmos. So let's say we take these two functions and we plug them in just as is. Once again, we look for those intersection points and we see our solutions right there, right? We've got 0, 3, boom, 4, negative 5. That's how you do it. Now, sometimes they're going to give you some question where they're going to say, solve for this constant, given that there's one solution, okay? So this one I think is best done by hand. So let me show you how I would do this. Let's say we have x squared minus 6x plus 3, and we've got y equals negative 2x plus c. So c is a constant, and we need to solve for c given that this system is supposed to have one solution. So let me show you how I'd go about doing this. Once again, I'm going to set them equal to each other. I'm going to bring 2x over, and I'm going to minus c. And now we have a nice quadratic equation. Now, this is the key. They're talking about the number of solutions. They said one solution. So again, that should make you think of the discriminant. So if we want one solution, we need our discriminant to equal 0. Well, now we got an equation. B squared minus 4ac has to equal 0. And my b is that negative 4, right? A is 1 in front of the x squared, and c is actually 3 minus c because both 3 and negative c, those are both constants, right? So that's the full c term. Now we're going to simplify and we're going to distribute that negative 4. So we've got 16 minus 12 plus 4c equals 0. 16 minus 12 is, of course, 4. 4 plus 4c equals 0. We'd minus 4 and divide by 4, and we've got c is equal to negative 1. So this is how you would solve a problem like this. Now, if you wanted to do this in Desmos, which I don't necessarily recommend because it can be a little bit tricky depending on the nature of the problem and the nature of the solution, right? Sometimes it could be a crazy wonky fraction, but you can use Desmos as follows, right? So we're going to, again, plug this into Desmos as is, and you're going to add a slider for C, or you can manually modify C as well. And you're going to keep tweaking C until you get this exact one solution, meaning one intersection point. Notice it's not touching it twice, just once. And again, we find the same answer. C has to equal negative 1 to get that single intersection point at 2, negative 5. Now we're on to radical, rational, and absolute value equations. So when we're solving radical equations, the way we'd carry it out is as follows. And by the way, a radical equation is where we have a radical like as follows, right? We have the square root of x plus 1. So we're going to start by getting rid of that square root. So we're going to square both sides. So again, now when we square the left side, we have x plus 1. It just destroys the square root. On the right-hand side, we have to FOIL it out, and we get x squared minus 10x plus 25. Now we're going to move everything over to the right-hand side, right? We're going to minus x, and we're going to minus 1, and we get x squared minus 11x plus 24. And now we factor, right? We've got x minus 3 and x minus 8. And we got two solutions, 3 and 8. But the thing about radical equations is you might get two solutions, but they might not both be legitimate solutions. We might have an extraneous solution. So we have to now plug these in and check. If I plug in the first one, 3 plus 1 is equal to 3 minus 5. 3 plus 1 is 4. So we say, does the square root of 4 equal negative 2? Now you might say, wait a minute. Isn't the square root of 4 plus or minus negative 2? In this case, for these rational equations, we're only thinking about the positive root. So this would not be true, which means that 3 is actually an extraneous solution, right? Square root of 4 would be positive 2. They're not equal, so that one is no good. What about 8? 8 plus 1 is equal to 8 minus 5. The square root of 8 plus 1 is the square root of 9. Square root of 9 is indeed 3. That passes the check. So 8 is a legitimate solution Done. Now, when it comes to rational equations, something like this, right? We have a fraction equaling a fraction. The way we would solve something like this is via cross multiplication. So 9 times 4 is 36, and then 3 times x plus 4 is going to give us 3x plus 12 as we distribute. Then we're going to solve like normal, right? We're going to minus 12 from both sides, and we get 24. Then we're going to divide by 3, and we get x is equal to 8. Finally, when we talk about absolute value equations, the main thing to remember here is you're going to get two solutions for the most part, unless the absolute value is set equal to 0, right? Then you're only going to get one solution. But in this case, absolute value of x minus 4 equals 6. Remember, the absolute value is a positive purifier. So as long as I have 6 or negative 6 within the absolute value bars, I got a legitimate solution, which means we can split this into two separate equations. As long as x minus 4 equals 6 or negative 6, we got a winner. So now we just solve these two equations. We add 4 to both sides and we get x equals 10. Add 4 to both sides, we get x equals negative 2. My two solutions are 10, negative 2, done. So another type of absolute value equation that is showing up in the digital SAT is something like this. We have an absolute value expression plus another one is equal to a constant. So how do you solve something like this? So on the digital SAT, they're kind of setting you up in a way that if you factor these expressions, it's going to make sense. So let me show you what I mean. So for 2x minus 4, for example, I can factor out a 2. So then I have 2 times x minus 2, like so in the absolute value. Here I can factor out a 3, right? So then I've got x minus 2, like so, right? In the absolute value, we got equal to 5. Now I can do some simplification, because when I got the 2 out here, I can actually pull it outside of the absolute value, because absolute value of 2 is 2. So it's not really changing anything to move it out. So now I've got 2 times the absolute value of x minus 2 plus, and I can do the same thing here, 3 times the absolute value of x minus 2 is equal to 5. Now it's like we have like terms, right? We have x minus 2 and x minus 2. So 2 of that plus 3 of that is 5 of that. So I've got 5 absolute value of x minus 2 is equal to 5. Now we can isolate the absolute value by dividing both sides by 5. And we have absolute value of x minus 2 is equal to 1. Now we do the split like I showed you guys in the previous slide. We've got x minus 2 is equal to 1, and we've got x minus 2 is equal to negative 1. Now we are going to add 2 to both sides here, and we got 1. We're going to add 2 to both sides here, and we've got 3. And we just solved it. My two solutions are 1 and 3, done. Now we're on to quadratic and exponential word problems. So when we're talking about quadratics, there are some things that we need to know in terms of their interpretation. So if we're talking about the y-intercept of a quadratic, that's going to be my answer to a starting point or an initial value for a word problem. Also, we have our x-intercepts. Those are the points of 0 value. So if they're saying, hey, at what point does the profit go to 0 or the revenue go to 0, we're talking about our x-intercepts. And finally, the vertex. This is another thing that they're going to ask about. It's either going to be the high point or the low point. When does revenue max out? When do we have a minimum in profit? So the max or the min value, they're talking about the vertex. Now again, just so we can see these two examples of these two different graphs, y-intercepts in red, right, where it hits the y-axis, the x-intercepts are where it hits the x-axis in blue, and of course the vertices are at the top or the bottom, either the high point or the low point, depending on the orientation of the parabola. Now when we talk about exponential problems, let's take another look again. Y-intercept starting point, right? We've got the rate of change. In this case, in the format of an exponential function, right, that rate of change is whatever we're adding to 1 or subtracting from 1 as well, right? We could have exponential decay where the values are getting smaller and smaller. Now, as we look at a graph, right, we again have the y-intercept where it hits the y-axis. And this is your typical shape of an exponential function where we are experiencing exponential growth. Now, let's talk about quadratic graphs, right? We're going to see parabolas. It's this U shape. It's either opening up or opening down, one or the other. Now, do we have to know the term parabola? No, but I'm just telling you that is the name of the shape. Now, what makes a quadratic a quadratic? It is all about the degree. The highest degree for a quadratic is 2, right? And we see that right there in that first term. Now, standard form of a quadratic, which is ax squared plus bx plus c, we can immediately see some cool information in standard form, which is that if I know the value of c, for this parabola, I know the y-intercept. So here's this parabola graphed out. And again, we see that y-intercept occurring at 0, -6. We also have another format, which is intercept form. And intercept form is pretty cool because we can tell where the x-intercepts are, right? It's where each of those zero out, each of these binomials. So at -3 and also at positive 1. Finally, we have something called vertex form. This is a very important format. By the way, a lot of times in the digital SAT, they're going to give you the vertex. You can use vertex form to therefore come up with an equation of the parabola. And maybe you might need to figure out what A is, but you can figure out the rest of the pieces. So for example, if we know the vertex, which is HK, we can plug it in, right? So for this one right here, I can tell you the vertex H comma K is the opposite of the 1, which is -1. And that -8 as is. So you can see the vertex right there at the bottom. And just to give you guys one more example of vertex form, we have this quadratic function. And if we were to graph this, we can easily see the vertex, which is going to be the opposite of -2, 3, which we can see right here at 2, 3 for the vertex. And by the way, this one is going down. It's opening down. And we know that it would be opening down because that A value is negative, right? So if we see a -2 or a -7 or whatever, we know the quadratic is opening down. Now, let's say we're given a quadratic in standard form like we see below, and we're asked to find the vertex. We can use this formula. The x value of the vertex is -b over 2a. So in this case, it's going to be -4 over 2 times 2, which is -4 over 4, which is -1. Now, to find the corresponding y value, you'd plug that -1 back into the function, and you'll see that we get a y value of -8. Now, let's talk about exponential graphs. So first of all, an exponential function in standard form is y is equal to a times b to the x, right? A is going to be the initial value. So if they say A at time 0, the population is 10,000, A should equal 10,000. B is the growth factor. If they say it's growing by 10%, it should be 1.1. If it's doubling, it should be 2. So in this case here, we have an initial value of 3 and a growth factor of 2, meaning it's doubling every time x increases by 1. And we can see the graph of this would look like this, right? This is your typical exponential growth going up from left to right. And notice we got a y-intercept at 0, 3. That is the initial value. That is the A. Now, again, we're talking about exponential growth. That B value is greater than 1. If we're growing by 5%, B is going to be 1 plus 0.05, the decimal equivalent of 5%. So here's an example of 5% growth with an initial value of 10, and we can see the graph would be right here. And that's what it would look like. Once again, y-intercept is the same as that A value. Now we could have exponential decay where we are losing value as x increases. And this is where B is going to be between 0 and 1, right? So if we're saying a decay of 5%, if we're losing 5% every time x goes up by 1, what are we retaining? We're retaining 95%, which is 0.95. So this is exponential decay of 5% with, again, an initial value of 10. And now the graph is going to go down from left to right. But notice we still have that nice y-intercept at 0, 10, the initial value. Finally, we're on to polynomial and other nonlinear graphs. So polynomial graphs, right? A polynomial function is technically a quadratic, is technically all sorts of things, but in this case, we've got something to the third power. And the important thing to know about polynomial graphs is when it's in factored form, we should be able to easily identify the zeros. So for example, here the zeros are whatever's going to make each of those binomials go to 0. We've got 1/4, 2, and 3. So how this is going to manifest in a graph is we're going to have a 0 at 1/4, 0, 2, 0, and 3, 0. Now, another quick thing to note, right? Since each of these are to the first power, you notice that in every instance, it's going through the graph, through the graph, through the graph. But if I were to square one of these, it's going to change what the graph is going to look like. It's no longer going to go through. We're going to see a bounce. Let me show you what this looks like in Desmos. So here's our same graph, and notice we've got the same zeros as we had on the slide. But now watch what happens. Let's say I raise x minus 2 to the second power. Everything else has stayed the same, right? We still have a 0 at 0.25. We still have a 0 at 3, and we still have a 0 at 2, but look at the different behavior. It's no longer going through at 2. It's now bouncing. It's ricocheting off and going back down, and then again, it's going through still at 3 and 1/4. Now, watch what happens when I change the 3 to a second power. So I get x minus 3. Let's raise this. And now that one's bouncing as well. So you can see when we have an even exponent like 2, it turns from going through when it's odd to bouncing when it's even. Now let's talk about graphs of rational functions, rational graphs, right? So let's say we have a graph like this, x minus 4 over x plus 3. The way we can graph something like this is by looking at the numbers on the numerator and the denominator. So this is what the graph would look like. And the key pieces of information are as follows. We know we have an x-intercept at 4, 0. Why? Because that's what's going to zero out the numerator. So there's our x-intercept at 4, 0. What about -3, which zeroes out the denominator? That is going to give us our asymptote, our vertical asymptote. This is not actually going to show up in the graph. It's an invisible line, an invisible boundary between those two curves. And then we also have 0, -4/3 for the y-intercept. Where did we get that? Again, the y-intercept is when x equals 0. So you just got to plug in 0 and you see these go away and we are left with -4/3, which we can see right there on the graph. So if we take one more example, right, x plus 2 over x minus 5, we can do the same thing. We have our x-intercept at whatever's going to zero out the numerator, which is -2 right there. We have our vertical asymptote at what's going to zero out the denominator, which is at x equal to 5, which is right here, x equals 5. And last but not least, we have the y-intercept, which occurs when we plug in 0 for x, which will give us 2 over -5 or -2/5, which is right here. And that's it for all the critical concepts on advanced math. And now we're going to move into the final category, geometry and trigonometry. Now we are on to critical concepts part 4 of 4, geometry and trigonometry. Let's do it. So let's go over the 6 subcategories of geometry and trigonometry. We have area and volume, congruence, similarity, and angle relationships, right triangle trigonometry, circle theorems, we have unit circle trigonometry, and last but not least, circle equations. All right, so starting off with area and volume, we have the given formulas. Now, it's very important to know the given formulas so you know what you don't need to have memorized. So we have all these great formulas, right? We have area and circumference of a circle. We have area of all these different shapes, special right triangles, and then we have the volume formulas of these 5 solids. We also have down here, they say the number of degrees in a circle is 360 degrees or 2 pi radians. And that's very important because that's going to tell you the equivalency between radians and degrees if you do forget it. And last but not least, we have the triangle angle sum theorem. Now, some of these things I'm still going to go over in the slides, but I just wanted to let you know that this is where you can find a lot of this information. So first, let's start out with volume formulas that are on that sheet, but we're going to go over them in detail. So first, we have a sphere, right? And we have 4/3 times pi r cubed to get the volume of a sphere. So the only thing you need to know is the radius. When we have a cylinder, we have a height and a radius. And to get the volume, it's pi r squared times the height. And for a prism, we could have a rectangular prism. We could also have a triangular prism. Again, a prism is just a shape that is extended, right? So it's like we have this base and it's extended up. Here for this triangular prism, we have a triangle that's kind of extended backwards by the length of the height. And so the general formula is the area of the base, whatever the base is, right? So here's a triangular base, here's a rectangular base, times that height, times the amount that it's being stretched. We also have a pyramid, which would look like this, and we got that height going straight to the top, down to the base, and it can be a square pyramid or a hexagonal pyramid, so on and so forth. And the general formula is 1/3 area of base times height. We also have a cone, which is kind of like a pyramid. It goes to a point, but it's a circular base. And this is 1/3 times pi r squared times h. Now, when we talk about surface area for the following shapes, I think it's important to go over these surface area formulas because they're not provided on the reference sheet. And I have seen them ask about surface area for some of these solids. So let's check it out. So for a sphere, it's simply 4 pi r squared. For a cylinder, it is 2 pi r squared plus 2 pi r times the height. And what you might recognize is that 2 pi r squared is going to give you the area of the top circle and the bottom circle. 2 pi r h is going to give you that lateral surface area, this amount going around the sides. When we're talking about a prism, okay, we're going to do the perimeter of the base times the height plus 2 times the area of the base, okay? When we talk about a pyramid, it's going to be 1/2 times the perimeter of the base times the slant height. That's this height coming down on one of the faces, right? That's the slant height plus the area of the base. Finally, for a cone, it is pi r times the slant height, once again, plus pi r squared, which is the area of the base. Now, of these surface area formulas, the ones that I've seen the most are just basic surface areas of prisms. Now, the cool thing about prisms is even if you forget that formula, you can just be like, all right, well, how can I calculate the area of every base as well as every face, and you just kind of add them up. Now we're going to go over some area formulas of two-dimensional shapes. We have a parallelogram, which is not provided on the reference sheet, but it's just simply base times height. We also have a trapezoid, which I don't think is likely to be tested, but I wanted to give it to you just in case. And we have the bases B1 and B2, which are parallel, and then we have the height, which is the distance between the two bases, and the area of the base is base 1 plus base 2 divided by 2 times height. Now I also wanted to go over the relationship of side length to both area and volume. So if we look at these two shapes here, right, these are both cubes. This is a cube with side length of 2 and a cube with side length of 3, right? And if we want to know, hey, what's the ratio of the surface area of both of these cubes? So we go back and we say, all right, well, the ratio of the side lengths is 2 to 3. To get the ratio of the surface areas, or the areas, we take the 2 and the 3 and we square them, right? And that's because, again, we're two dimensions, so we're taken to the second power. So the ratio of the surface areas should be 4 to 9. Now, if we actually calculate the surface area, each face here is 4, right? 2 by 2, which is 4, and there's 6 faces, which gives us a surface area of 24. Here, we have 3 by 3. Each face is 9 times 6 is 54. Now, if we were to divide both of these by 6, we'd get a 4 to 9 ratio, which we predicted over here. Now, the volume will be going back to the side length, we're raising it to the third power, so we should have a ratio of 2 to the third to 3 to the third, which is 8 to 27. And if we actually calculate the volumes here, it's 2 times 2 times 2, which is exactly 8. Here it's 3 times 3 times 3, which is exactly 27. So just something to keep note of. When we know the side length of two proportionate 3D figures, we can get the ratio of both the surface area and the ratio of the volume using this process. Now we're on to congruence, similarity, and angle relationships. So first of all, what is congruence? What does that word mean? It means identical, right? So if we have two shapes that are congruent, they are exactly the same. They have the same side lengths and the same corresponding angle measures. So these are two examples of congruent shapes. Now, what about similarity? Similarity means proportionate. So for example, we might have different side lengths, but the angle measures are all going to be exactly identical, and the side lengths are going to be extended by a common factor. So for example, in this one, it looks like the larger pentagon, each side length is exactly double or approximately double the side lengths of the smaller pentagon. And again, here we have similar figures. We've got this octagon and then a shrunk down to scale octagon. And just to reiterate the main tenets, the sides are proportionate, but the angles are congruent with similar shapes. Now, what about congruent triangles? We need to know how to prove congruent triangles. A lot of times they'll give you a little bit of information about two triangles, and they'll say, which piece of information additionally do we need to show that these two triangles are congruent? So again, we can show congruent triangles in 5 different ways. We can show it with side, 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 meaning showing that all 3 sides are congruent. We could show it via side, angle, side, where we've got 2 congruent sides, and the angles in the middle are also equal or congruent. We've got angle, side, angle, 2 congruent angles, and the sides in between are congruent. It's got to be in that order. We've also got angle, angle, side. So any 2 angles are congruent, and then a corresponding side is congruent. And last but not least, if we have 2 right triangles, we can prove that they are congruent just by showing that the hypotenuses are congruent as well as one of the legs. Next, we want to be able to show how to prove triangles are similar. So we've got 3 ways to prove triangles are similar. First of all, we have angle, angle similarity, the most commonly used theorem. If we can show that 2 angles and 2 triangles are congruent, the triangles have to be similar. We also have side, angle, side, where we have an angle that is congruent and the sides surrounding that congruent angle are going to be not congruent, but proportionate. So again, AB to XY is the same as AC to XZ, those sides around those congruent angles. And then last but not least, we have side, 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 which means that all 3 sides are proportionate in the exact same way. Next, we have the triangle angle sum theorem, which is again on the reference sheet, but let me explain a little bit more detail what it means. It means that for any triangle, if we have 3 angles, they must add up to 180 degrees. Applying the triangle angle sum theorem to a right triangle, if we have 2 unknown angles and a right angle, well, since they all add up to 180, these 2 other acute angles must therefore add up to 90. And that makes sense because those 2 adding up to 90 plus this remaining 90 will bring us back to 180. We also want to know the term complements and supplements. Complements are any 2 angles that add up to 90 degrees. So we can see right here, X and Y would be complementary because together they form a right angle. An example would be 15 and 75. Another example would be 30 and 60. Supplements are angles that add to 180 degrees. So we'll often often see this on a straight angle or a straight line, right? We have W and Z. So here W and Z add up to 180. So an example could be 30 and 150 or 95 and 85. Now we're going to talk about angle relationships with parallel lines. So these are very important. We've got two lines that are parallel, and we know they're parallel because of these markings, right? And then we got a transversal, a line that's hitting both of these parallel lines. And now we got these different angle markings, 1, 2, 3, 4, 5, 6, 7, 8. And we've got angle relationships that are true because these lines are parallel. So let's talk about these angle relationships. First of all, we have corresponding angles, and corresponding angles are congruent. Corresponding angles are angles that basically, if you slide down the transversal, they're in the same position for the first line as the second line. So for example, 2 is corresponding as we slide down with 6. 1 is corresponding with 5. 3 would slide down to 7, and 4 would slide down to 8. So we have the following relationships: 2 and 6, which are congruent; 4 and 8, which are congruent; 1 and 5, and 3 and 7, all of these are congruent. We also have alternate interior angles. Alternate because they're on opposite sides of the transversal. Interior because they're on the inside of these two parallel lines. So we have 3 and 6 and 4 and 5. And in both cases, they are equal to each other. We also have alternate exterior angles. Now we're alternate sides of the transversal, but on the outside of the parallel line. So we have 1 and 8 and 2 and 7. And again, they are congruent. 1 is congruent to 8. 2 is congruent to 7. Then we have consecutive interior angles, okay? Interior, again, on the inside, and consecutive right next to each other, 4 and 6, 3 and 5. But these have a different relationship. These are supplements, meaning they add up to 180, right? So 4 and 6 and 3 and 5, those two pairs, they add up to 180. Then we have vertical angles. This doesn't have to do with the parallel lines, but just opposite the crisscross, right? We have two lines crisscrossing. Vertical angles would be 7 and 6, also would be 5 and 8, 1 and 4, and then also 2 and 3. And vertical angles, they are all congruent. Now, one last thing to note, when we have two parallel lines, just look, we only have two possible outcomes. Two angles would be congruent or supplementary. Now, one thing that I didn't include here is same side exterior angles. This is just like consecutive interior angles, 2 and 8, 1 and 7. And those also have a supplementary relationship, meaning they add up to 180. Now, the way you could also deduce that if you forget that relationship is just say, well, 2 and 8, they definitely don't look equal. And I remember that I had two possibilities, congruent or they are supplements. So if they don't look congruent, they're probably adding up to 180. Next, we are on to interior angles of polygons, and there's a formula here, n minus 2 times 180, that gives us the sum of the interior angles of any polygon. And I do see this occasionally pop up on some of the practice tests, so I do think this is a pretty important formula. And n is equal to the number of sides of the polygon. So for example, if we have a triangle, n would be 3. 3 minus 2 is 1 times 180 is 180. Now, if it is a regular polygon, meaning all the sides and angles are congruent, right? Equilateral, equiangular, each angle, individual angle would be 60 degrees. Now we can apply this to any other polygon, right? You just plug and chug. To get the total number of angles for an octagon, you plug in 8 for n. 8 minus 2 is 6. 6 times 180 gives you 1,080. And so on and so forth. Now, you could memorize these angle sums, but I wouldn't recommend it. I think the best way is to memorize the formula and then apply it as need be. Now, when we're talking about exterior angles of polygons, this is pretty cool because it's a singular rule, which is that for any polygon, the sum of the exterior angles is always 360. So we can see here with this pentagon, all the exterior angles are 72. They add up to 360. With the hexagon, all the exterior angles are 60. And since there's 6 of them, again, it's adding up to 360. So no matter what, exterior angles of any polygon add to 360 degrees. You may also have to convert back and forth between degrees and radians, and the way you can do that is as follows. We got this nice little chart, right? 30 degrees is equal to pi 6 radians, 90 degrees is pi halves, and so on and so forth. But the main thing you want to be aware of is 180 is equal to 1 pi, or as they put it on the reference sheet, 360 degrees is equal to 2 pi. That's going to allow you to convert back and forth with a nice conversion ratio. So for example, if you're going from degrees to radians, you're going to take your degree value as theta and multiply it by pi over 180, right? The radians value over the equivalent degrees value. Conversely, if you're going from radians to degrees, you're going to take your theta value and multiply it by the reciprocal of that, 180 over pi. Next, we're on to right triangle trigonometry, and we're going to start with Pythagorean's theorem. Again, this is on the reference sheet, but I wanted to put it here so I could explain it in a little bit more detail. Pythagorean's theorem is a squared plus b squared equals c squared for any right triangle where a and b are the legs and c is the hypotenuse. So we can kind of see an image of this, right? If we square each of those side lengths, a squared and b squared are going to give us c squared. As an example, if we had a 3, 4, 5 right triangle, we'd know that 3 squared plus 4 squared would have to equal 5 squared, which is indeed true, right? We get 9 plus 16 is equal to 25, which is correct. Boom, done. Now, using Pythagorean's theorem for a triangle, we can solve for missing sides. So let's say we know the leg is 5 and 12. To find c, we can plug and chug, right? 5 squared plus 12 squared should equal c squared. 5 squared is 25, 12 squared is 144. Add them together, that's 169. Now we take the square root of both sides and we get c, which is the hypotenuse, is equal to 13. We can also use Pythagorean's theorem to solve for a leg. So let's say we know a leg is 7 and the hypotenuse is 25. Our missing leg is b. And by the way, what you call a and b is more or less irrelevant, but I happen to be using a as a small leg here. So let's plug and chug. We got 7 squared plus b squared is equal to 25 squared. That's 49 plus b squared is equal to 625. We're going to subtract 49 from both sides, and we get b squared equals 576. We're going to take the square root of this, and we get b is equal to the square root of 576, which is 24. Boom, done. We're also going to cover special right triangles, which is again on the reference sheet, but let me show you how they work. In particular, we're going to have two that are going to show up on the SAT, which are 45, 45, 90s. And the relationship of the side lengths are as follows. If we know the legs are x, and they're going to be the same, right? Because if the two angles are equal, the two corresponding side lengths are going to be equal. And the hypotenuse will also always be that little leg times square root of 2. We also are going to have a 30, 60, 90. Here, it's all about the little leg. The little leg, which is opposite the 30, is x. If we know that, we can get the big leg and the hypotenuse, because the big leg is x times square root of 3, and the hypotenuse is double the little leg, which is 2x. Now, using these relationships for 45, 45, 90, we can solve the following triangle. So let's say we know the little legs are 3. We can get the hypotenuse by taking that little leg and multiplying it by the square root of 2 to get 3 rad 2. Likewise, for a 30, 60, 90, if we know that the little leg is 6, we can take that little leg, multiply it by rad 3 to get the big leg, and then we take the little leg and we double it to get 2x, which is 12. So again, with that color coding, you can see how all of the different side lengths connect back to the original ratios. Next, we need to talk about SOHCAHTOA. Now, this is about all the trig that you need to know to be successful on the math portion of the digital SAT. So what is SOHCAHTOA? SOHCAHTOA is going to tell us how to use our three basic trig functions, which are sine, cosine, and tangent, okay? So, S-O-H, means sine of an angle is equal to the opposite side over the hypotenuse. Opposite side meaning opposite leg. So here, if we're taking sine of angle A, it's equal to the blue leg over the green hypotenuse. If we're taking cosine, that is equal to adjacent over hypotenuse. So cosine of A is equal to the adjacent side length, and that is the leg in brown over the hypotenuse in green. Last but not least, we have tangent TOA, which is equal to opposite over adjacent. So tangent of A would be the opposite leg in blue over the adjacent leg in brown. Now, using SOHCAHTOA, we can solve for sine, cosine, and tangent of theta with the following side lengths. So sine of theta is opposite over hypotenuse, which is 5 over 13. Cosine of theta would be adjacent over hypotenuse, 12 over 13, and tangent of theta is opposite over adjacent leg, which is 5 over 12. So again, it depends on which angle you're running through these trig functions. That will dictate the ratio that you get. Another good rule to know for trigonometry is that sine of an angle equals cosine of the complement of that angle. So sine of 10 would equal cosine of 80. Again, complements are two angles that add up to 90 degrees. We also have sine of 30 is equal to cosine of 60, and so on and so forth. Now, I could come up with infinite examples here, but these are just a handful to show you this relationship. Sine of an angle equals cosine of a complement. Now, in this case, using sine of an angle equals cosine of a complement, since we talked about right triangles already, and we said that these two acute angles other than the right angle are going to be complements. If we have a diagram like this, we know that sine of angle A is equal to cosine of C. Likewise, sine of angle C is equal to cosine of A. So we can go either direction. Next, we're going to talk about mean proportionals in right triangles. I have been seeing this show up on the digital SAT. So what does this mean? We're talking about a right triangle, which is the big right triangle, where we drop in altitude down to the hypotenuse. So what this does is it actually makes three right triangles. We have one, we have two, which is the medium-sized one, and then of course we have the big dog. And the cool thing is these three right triangles, they're not only right triangles, but they're similar right triangles. They're all similar to each other, which is really cool because we can then create the following relationships. I know that little leg of the little triangle over medium leg of the little triangle is equal to little leg over medium leg of all the other triangles. So for the medium-sized triangle, we have little leg F over medium leg D, and then it's also equal to the little leg and medium leg of the big triangle, A over B. Okay, so that's one relationship. And we also can say little leg over hypotenuse is equal to little leg over hypotenuse, little leg over hypotenuse, which is C. So all of those are going to be equivalent. Last but not least, we have medium leg over hypotenuse. So that's for the little triangle. Then D over B is for the medium triangle. And for the big dog, we have big leg over hypotenuse, B over C. So it's very important to know these proportionate relationships. Now, again, you don't have to write all of this down and write down these particular equations, but just remember, they're proportionate. So if you get matching parts over matching parts, they should be equivalent. So first of all, let's go over some circle terms. So we have our general circle, and just so you know, again, you're not going to necessarily have to recall these terms, but it's good to know them so when they ask for circumference, you know what you're calculating. So circumference is the length going all the way around the circle. Then we see the center, which is right here, denoted by B. And notice everything is color-coded. Then we see the radius, which is the distance from the center out to any edge. Then we have the diameter, which is going from edge to edge through the center. Then we have something called a chord. That's just going from edge to edge. Now you might say, well, isn't a diameter technically a chord? We would say, yes, it is. It's just a chord that's going through the center. Then we have something called a sector. This is like a slice of pizza, right? It's the area of a slice of the circle. Then we have a secant. This is a line going through the circle. Next, we have a tangent, which is something that is just going to touch the circle at one point. Now, an important fact to note is when we have a tangent to a circle, it is perpendicular to the radius where it touches that radius. And last but not least, we have a segment. So a segment is kind of like the crust of the pizza. So you notice we have that section there where we draw a line across from one edge to the other of the circle and fill in that area. Now, the circle equations that are given, you get circumference in the reference sheet, but I'm giving it anyways. Circumference is equal to 2 pi r. We also have area is equal to pi r squared. Both of these formulas are given. What's not given is the arc length. Now, arc length is simply a fraction of the circumference, and we get that fraction by taking the central angle over 360. Likewise, for the area of the sector, we do the same thing. We take the area of the entire circle, pi r squared, and multiply it by that same fraction, n over 360, n being the central angle of that sector. Now we talk about arc measure compared to arc length. Arc measure is going to be in degrees or radians. So it's not a measurement of length, it's degrees or radians. And it's going to be equivalent to the central angle. Now if instead it's cut out from an inscribed angle, it's going to be double the inscribed angle. So let me give you some examples here. So let's say we've got the circle, we've got AB as our arc measure, and to find that arc measure, if I see the central angle that cuts that out is 50 degrees, I know my arc measure of AB is 50 degrees. Likewise, if I have AB here, and now I have this inscribed angle, ACB. So if ACB is 25, that means the measure of arc AB is double that angle measure, which is 50 degrees. Now, when we talk about circle tangents, again, tangent line is perpendicular to the radius. So I just want to make this absolutely clear, even though I quickly mentioned it in an earlier slide. So if we have a circle like this, we have a center here, we have a radius come out. If we have a tangent touch the radius, right? Coming through and touching that radius right at that point, it's going to form a 90-degree angle. Another important thing to note, external tangents from the same point are congruent. So check this out. We have a circle, we have a common point here, and we got two tangents coming out and touching that circle, right? Once again, these external tangents are going to be equal in length. And once again, just to reinforce this point, if we touch tangents at those points, we're going to form right angles. Now we're going to do some unit circle trigonometry. So once again, just so we have a rough understanding of the signs in each quadrant, we have quadrant 1, 2, 3, and 4, it's important to remember that in quadrant 1, angles 0 through 90 will exist. In quadrant 2, it's going to be 90 through 180. And by the way, the equivalent radians for 0 to 90 is 0 to pi halves. The equivalent radians for 90 to 180 is pi halves to pi. Quadrant 3, we're in angles from 180 to 270, or in radians pi to 3 halves. 3 halves pi. And finally, in quadrant 4, we have 270 to 360, or in radians, 3 pi halves to 2 pi. Now, depending on what quadrant we're in when we're taking trigonometric functions, it's going to determine the sign of the outcome of that trig function. Now, a nice little acronym to remember is all students take calculus. So what this means for all is in quadrant 1, sine, cosine, and tangent are going to return positive values for any angle between 0 and 90. Students is S, that represents sine. That means in quadrant 2, sine is positive, but everything else is negative. In quadrant 3, for the take, tangent is positive, but everything else is negative. And in quadrant 4, cosine is positive and everything else is negative. Now, the good news is you can also use a calculator to verify if you're taking sine, cosine, or tangent of an angle in a different quadrant, whether it's positive or negative, but this is a quick and handy way to remember. Now, if we get some examples, sine of 120 is going to be positive because 120 is going to be in quadrant 2. Sine of 195, however, that's going to be in quadrant 3. That's where tangent is positive, but sine will be negative. Tangent of 220, again, quadrant 3, positive, but tangent of 330 is quadrant 4, that's going to be negative. Finally, cosine of 335 in quadrant 4, that's positive, and cosine of 135 up here in quadrant 2 will be negative. Now I'm going to do a quick discussion of the unit circle, but again, you don't have to have this memorized. If you do know it and can reference it, it can save you a little bit of time, but it's not essential. So when we look at the unit circle, the way we want to think about it is if I'm taking sine of an angle, that is going to return the y value of a corresponding coordinate. If I'm taking cosine of an angle, it's going to return the x value of that coordinate. And tangent is going to be the ratio of y over x. Let's go through some examples. So if I'm taking sine of 45, it's going to be the y value of that coordinate at 45 degrees, which is right here. So you can see that's what it corresponds with. Likewise, if I have cosine of 150, which is out here, it's going to correspond with the x value of that coordinate. Finally, tangent of 240 down here is going to correspond to the ratio of negative rad 3 over 2 divided by negative 1/2, right? It's that full coordinate and the ratio of y over x, which simplifies to positive rad 3. Finally, we're on to circle equations. So what is the circle equation? Here is standard form, x minus h squared plus y minus k squared equals r squared. And where the center is h comma k and the radius is r. So whatever constant we have on the right side, the square root of that is going to be the radius. So for example, we have the center hk and this is radius, which is r. So again, we have our standard form at the bottom. So let's say we have this equation, x minus 3 squared plus y minus 4 squared equals 25. We know that the center is at 3 comma 4 and the radius is the square root of 25, which is 5. So if we were to graph this out on a coordinate plane, there's our center at 3 comma 4 and we can see the radius is a length of 5. Now you might also get an example like this where it's not in standard form. So there's a couple ways you can go about figuring out the center and the radius. So the first option is we could put this into standard form. So to do this, we're going to do a little bit of completing the square. So we're going to group the x's, group the y's, and have that constant on the other side by itself. Now we're going to complete the square. So for the x's, I'm going to take half of this middle coefficient, which is 2, and I'm going to square it, which is 4, and I'm going to add it to both sides. Then I'm going to take half of this negative 8 for the y term, which is negative 4, square that, and add that to both sides. So that's 16 added to both sides. Now I've created a perfect square here and a perfect square trinomial here. Negative 11 plus 4 is negative 7 plus 16 is 9. So on the left-hand side, we're going to take these two perfect square trinomials and we're going to factor them. This one's going to become x plus 2, x plus 2. This one's going to become y minus 4, y minus 4. And they are perfect squares, which is what we wanted. And as I mentioned on the right-hand side, we're going to get 9. Now I can write this as x plus 2 squared and y minus 4 squared is equal to 9. Now we got it in standard form. Now we can figure out everything about the circle. So I know my center is at negative 2. positive 4, right? The opposite of this and the opposite of that. And my radius is going to be a square root of 9, which is a length of 3. Boom, done. So now we're going to take the same equation. I'm going to show you another way to find the center and the radius using Desmos. So first of all, we're just going to plug it into Desmos just like it is. We're not going to change anything. Now, if we want to find the center, for example, I'm going to look at these 2 points right here that have been highlighted, right? And Desmos will do that automatically for you. You just have to click on the very top and the very bottom points. So now I see I have a top point of -2, 7 and a bottom of -2, 1. So if I want to find the radius, I just look at the distance between these two, right? So I'm not moving anywhere on the x-axis, so I'm just taking the distance between 7 and 1, which is 6, and that would give me the diameter. So the radius is half of the diameter, so I'm dividing that by 2, and we get a radius of 3. Now the center is going to be the midpoint of these 2 points, right? Again, -2 and -2. So the x value is going to be -2, but the y value is going to be the average of 7 and 1. 7 plus 1 is of course 8, divided by 2 is 4. So we have a final center coordinate of -2, 4. That is it for all of the critical concepts that you need for the math portion of the digital SAT. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.